In the vast history of our solar system, one giant has shaped the orbital ballet of nearly everything around it. A world so large it contains more than twice the mass of all other planets combined. This is Jupiter. Yet, the most compelling story in its system may not be about the planet itself, but about one of its moons, a small, frozen world that could hold the answer to one of the fundamental questions we have ever asked. Is life on Earth a singular event? Welcome to the Science for Deep Sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. This is a journey from a known giant to a hidden ocean. We will travel not just through space, but through the process of scientific discovery itself, peeling back layers of gas, ice, and long-held assumptions. We begin with the immense power of Jupiter, the gas giant that anchors our solar system. Then, we venture toward the tantalizing possibility of a vast, concealed ocean on its moon Europa, a place where the next great chapter in biology could be written. We will explore Jupiter's ocean, where science and mystery converge. The King of Worlds, a profile of Jupiter. Before we can understand the potential of its moons, we must first understand the planet they orbit. Jupiter is less a single planet and more the center of its own miniature solar system, a gravitational anchor dictating the motion of everything in its vicinity. Its scale is difficult to comprehend. If you were to line up 11 Earths, side by side, that chain of worlds would only just stretch across Jupiter's equator. Data from NASA's Juno spacecraft, in orbit since 2016, has allowed scientists to refine these measurements. Using a technique called radio occultation, where signals from Juno are passed through Jupiter's atmosphere back to Earth, we've learned that the planet is slightly more flattened at its poles than previously thought. Still, its equatorial radius is a staggering 71,492 kilometers. Every other planet in our solar system could fit inside it, but its size is secondary to its mass, which is where its true dominance lies. It is 318 times more massive than Earth, and its gravitational influence is so profound that the center of mass between it and the Sun, the barycenter, lies just outside the Sun's surface. In a very real sense, Jupiter's orbit causes the Sun itself to wobble. This gravitational dominance is paired with a remarkable rotation speed. A day on Jupiter lasts less than 10 hours. This rapid spin causes the planet to bulge at its equator, making it the most oblate, or visibly squashed, planet in our solar system. It is a dynamic, churning world of extremes. Its atmosphere is a planet-sized ocean of gas. The upper layers are composed of about 90% hydrogen and 10% helium, with trace amounts of other compounds like ammonia creating the planet's distinct, swirling colors. There is no solid surface. As you descend, the gas gradually thickens as pressure and temperature rise to immense levels, until the hydrogen itself is compressed into a state not found naturally on Earth. The visible surface is a tapestry of bands and storms. The lighter-colored bands are called zones, and the darker ones are belts. These are jet streams flowing in opposite directions at speeds over 360 kilometers per hour. Within these streams, colossal storms form. The most famous is the Great Red Spot, an anticyclonic vortex wider than our own planet. It has been observed for at least 300 years, a crimson eye in the clouds. We have watched it shrink over the decades, its shape becoming more circular and its color fading to a paler orange. Recent observations have also revealed that the storm's winds are changing speed, a rhythmic cycle that scientists are still working to understand. It is a weather system on a scale that defies terrestrial comparison. Deeper still, the mystery of Jupiter intensifies. Below the clouds, the pressure builds to millions of times that of Earth's atmosphere. Eventually, the hydrogen is compressed so intensely that its electrons are stripped away, and it begins to conduct electricity like a metal. This is the realm of liquid metallic hydrogen, a vast, churning ocean of fluid that constitutes the bulk of Jupiter's interior. The rotation of this metallic ocean is what generates Jupiter's magnetosphere, the largest and most powerful magnetic field of any planet, a structure so vast that if it were visible in our night sky, it would appear larger than the full moon. At the very center, scientists theorize a dense core of heavier elements may exist, but the conditions are so extreme, with temperatures hotter than the surface of the Sun, that we can only model what might lie in the planet's heart. The cosmic architect and a questionable guardian, Jupiter's influence extends far beyond its atmosphere. Its gravity acted as a sculptor for the early solar system. As the planets were forming, it is thought that Jupiter's gravitational perturbations cleared out primordial debris from what is now the asteroid belt. It also corrals thousands of asteroids, known as the Trojans, into stable orbits preceding and following it. The map of our solar system is, in many ways, a direct consequence of Jupiter's existence. This has led to a popular narrative: Jupiter as our cosmic shield. The theory is straightforward. Jupiter's immense gravity deflects comets and asteroids that might otherwise be on a collision course with Earth. The most visceral evidence for this occurred in 1994, when fragments of the comet Shoemaker-Levy 9 slammed into Jupiter's southern hemisphere. Astronomers watched as a series of impacts left dark, Earth-sized blemishes in the cloud tops, a demonstration of the protective role Jupiter can play. However, as our ability to model the complex dynamics of the solar system has improved, this simple narrative has become more nuanced. Recent computer simulations have revealed a dual role. While Jupiter does deflect many long-period comets arriving from the outer solar system, its gravity can also act as a slingshot, flinging asteroids from the main belt into the inner solar system and onto trajectories that could cross Earth's orbit. So, is Jupiter a guardian or a gateway for threats? The answer appears to be both. It acts as a chaotic filter, reducing the overall frequency of impacts from deep space while possibly increasing the risk from closer asteroids. Its presence likely contributed to the long period of stability needed for complex life to evolve on Earth by lowering the rate of cataclysmic events. But it also serves as a reminder that the solar system is a dynamic place, where the same forces that create stability can also introduce chaos. This influence is not limited to gravity. Jupiter's colossal magnetosphere, born from its metallic hydrogen core, deflects the solar wind and creates the most powerful auroras in the solar system. While this shield does not protect Earth directly, it governs the entire electromagnetic environment of the Jovian system, a system filled with dozens of moons, each a unique body in its own right. And it is here that our journey turns. The transition to intrigue, the Galilean moons. Orbiting Jupiter is a miniature solar system with over 90 known moons. Most are small, captured objects. But 4 are large enough to be seen from Earth with a small telescope. These are the Galilean moons, discovered by Galileo Galilei in 1610, a discovery which demonstrated that not everything orbited the Earth. Closest to Jupiter is Io, the most volcanically active body in the solar system. It is caught in a gravitational tug-of-war between Jupiter and the other large moons. This constant tidal flexing generates immense frictional heat in its interior, fueling hundreds of volcanoes that erupt with sulfurous plumes, painting its surface in shades of yellow, red, and black. Io is a world of fire, a testament to the raw power of Jupiter's gravity. Farthest of the 4 is Callisto, a dark, ancient, and heavily cratered world. Its surface is a frozen record of billions of years of impacts. Yet, magnetic field data from the Galileo spacecraft hinted that even beneath this battered crust, a deep, salty ocean might be present. Next is Ganymede, the largest moon in our solar system, larger even than the planet Mercury. It is a world of contrasts, with old, dark regions alongside younger, grooved terrain. Ganymede is the only moon known to generate its own magnetic field and is also believed to harbor a massive internal ocean, likely situated between thick layers of ice. But it is the second moon out from Jupiter, the smallest of the four, that commands our attention. At first glance, it is an unassuming, pale sphere, crisscrossed with dark lines. It is the smoothest solid object in the known solar system, with very few craters. This is Europa, and it is here, beneath this deceptively placid exterior, that the real mystery begins. The jewel of Jupiter, Europa's icy veil. When the Voyager spacecraft returned the first close-up images of Europa in the 1970s, scientists were perplexed. An ancient world should be covered in craters. Europa's eerily smooth surface suggested it was geologically young, somehow being constantly resurfaced. Its most prominent features were a complex web of cracks and ridges, called lineae, that resembled fractures on a shattered pane of glass. What could be erasing the craters and cracking the surface so uniformly? The answer appears to be the same force that powers Io's volcanoes, gravity. Europa is tidally locked with Jupiter, and as it orbits, it is constantly stretched and squeezed. This tidal flexing generates heat in its interior, much like a paperclip warms when bent back and forth, but on a planetary scale. This energy source is not enough to create volcanoes, but it is enough to warm Europa's interior far from the sun. This heating led to a revolutionary hypothesis. Perhaps there was enough heat to maintain a layer of liquid water beneath the icy shell. Suddenly, the strange surface features began to make sense. A young surface could be explained by liquid from below welling up and freezing, paving over older craters. The long cracks could be fractures in the ice shell caused by the stress of tidal flexing. Later observations from the Galileo spacecraft in the late 1990s and early 2000s provided strong evidence for this hypothesis. The key data came from its magnetometer, which detected an induced magnetic field around Europa as it passed through Jupiter's powerful magnetosphere. A secondary field like this is best explained by the presence of a global layer of electrically conductive material. The most plausible candidate for that conductor is a large, salty, liquid water ocean. The evidence continued to build. Scientists observed chaos terrain, jumbled landscapes that look as if large sections of the crust have broken apart, shifted, and refrozen, like icebergs in a polar sea. These are best explained by a subsurface ocean interacting with the ice shell above. Furthermore, the Hubble Space Telescope has on multiple occasions detected what may be faint plumes of water vapor erupting from Europa's surface, potentially offering a way to sample the ocean without drilling through the ice. The scientific evidence points to the existence of a vast, hidden sea. Our journey from this point is into that sea, and if you find the process of this discovery as fascinating as I do, I hope you'll continue on with us. The revelation, diving into the hidden ocean. Let us descend. Below the frigid, radiation-bombarded surface, we pass through the ice shell. Its thickness is one of the biggest open questions, with estimates ranging from a few kilometers to over 30. But somewhere below, the solid ice is expected to give way to liquid. Welcome to what may be the largest ocean in the solar system. Based on magnetic field data and density models, scientists estimate this global ocean could contain more than twice the liquid water of all of Earth's oceans combined. It is an ocean of total darkness, sealed under a thick roof of ice. What is this ocean made of? The induced magnetic field suggests it is salty. The reddish-brown material staining the surface cracks is thought to be salts, like magnesium sulfate, brought up from the ocean and altered by Jupiter's intense radiation. This suggests the ocean is not pure water, but a complex chemical solution. Critically, this ocean is believed to be in direct contact with a rocky seafloor. This is a significant detail. Here on Earth, in the deepest parts of our own oceans, entire ecosystems exist without sunlight. At hydrothermal vents, seawater circulates into the planet's crust, becomes heated, and erupts back into the ocean, carrying dissolved minerals. Life here does not use photosynthesis, it uses chemosynthesis. Microbes convert these chemicals into energy, forming the base of a food chain that supports a variety of organisms. Could a similar process be happening on the seafloor of Europa? The tidal heating that keeps the ocean liquid could also drive geological activity on the seafloor, possibly creating hydrothermal vents. This would provide two of the three key ingredients for life as we know it: a source of chemical energy and the raw chemical building blocks dissolved from the rock. Models suggest such vents could be stable for billions of years, continuously supplying the ocean with the materials necessary for life to emerge and survive. The possibility, the ingredients for life. Astrobiologists look for three primary things when assessing a world's potential to host life: liquid water, essential chemical elements, and a source of energy. Europa appears to have all three. First, a global ocean of salty liquid water. Second, energy. While sunlight is absent, tidal heating from Jupiter could power chemistry in the ocean and potentially drive hydrothermal vents. The third ingredient is chemistry, the elements essential for life, including carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These were likely present when Europa formed and would have been delivered by impacting comets and asteroids. A major question has been about the availability of oxidants like oxygen, which many organisms on Earth use for metabolism. In Europa's dark ocean, where would they come from? One source may be the radiation that constantly strikes Europa's surface. This radiation splits water ice molecules, hydrogen oxide, into hydrogen and oxygen. The light hydrogen gas escapes to space, but the oxygen and other oxidants can remain trapped in the ice. For a long time, it was unclear how these chemicals could reach the ocean below. However, scientists have modeled a fascinating mechanism. It is proposed that regions of the ice shell rich in these salts and oxidants could become denser than the surrounding purer ice. Over long timescales, these dense pockets of ice could slowly sink, or drip, through the ice shell, eventually reaching and dissolving into the ocean, providing a slow but steady delivery of these useful compounds from the surface to the hidden sea. Furthermore, a reanalysis of old data from the Galileo mission found evidence of ammonia-rich compounds near fractures on the surface. Ammonia is a potent source of nitrogen, another element crucial for building amino acids and DNA. Its presence suggests a chemically rich interior, further strengthening the case for a habitable environment. We now have liquid water, multiple energy sources, and plausible pathways for the necessary chemical ingredients to mix in a vast, stable ocean. The stage is set. The future, the next chapter in exploration. For all we have deduced, our knowledge remains indirect. The logical next step is to send a new generation of robotic explorers. Two missions, in particular, carry our hopes for understanding Europa. The first is NASA's Europa Clipper. Launched in October 2024, it is the largest planetary science spacecraft NASA has ever built. In early 2026, it is on its way back toward our planet after a crucial gravity-assist flyby of Mars in December 2025. In late 2026, it will swing by Earth for a final gravitational slingshot, giving it the velocity needed for the long journey to Jupiter, where it is scheduled to arrive in April 2030. Clipper will not orbit Europa directly due to the intense radiation. Instead, it will enter a long orbit around Jupiter and perform nearly 50 close flybys, some as low as 25 kilometers above the surface. Its 9 instruments include an ice-penetrating radar to measure the ice shell's thickness, a magnetometer to refine our understanding of the ocean's depth and salinity, and high-resolution cameras to map the surface geology. If it is fortunate, it may even fly through a water vapor plume, directly sampling the ocean's chemistry. Joining it will be the European Space Agency's JUICE mission, or Jupiter Icy Moons Explorer. Launched in April 2023, JUICE is also on a long path to Jupiter, arriving in July 2031. It will study Jupiter and conduct flybys of Callisto and Europa, but its main objective is to eventually become the first spacecraft to orbit another planet's moon when it enters orbit around Ganymede in 2034. Together, these two missions will revolutionize our understanding of these icy worlds. They are not equipped to find life, but they are designed to definitively answer the question of Europa's habitability. They will tell us if the conditions are truly right and if the ingredients are present. They will complete the necessary reconnaissance before humanity takes the next step, perhaps with a lander or a probe designed to melt its way through the ice to finally search for life in that dark, alien ocean. The grand mystery. Our journey has taken us from the churning atmosphere of the solar system's largest planet to the frozen crust of one of its moons. We have followed the scientific process, from the first puzzling observations to the compelling evidence for a hidden world. Jupiter, the chaotic giant, has shaped this entire story. Its gravity provides the energy that sustains an ocean far from the Sun. Its radiation may provide the very chemicals needed for life to exist in that ocean. In the coming decade, we will learn more about Europa than in all of history. Finding any form of life there would be a profound discovery. It would suggest that life is not a rare accident unique to Earth, but a common phenomenon that can arise in quiet, hidden places throughout the cosmos. The exploration of Jupiter's ocean is an exploration of our own place in the universe. The answer to the question, are we alone? May be waiting for us, moving silently in the dark depths beneath Europa's ice. Thank you for joining this journey. What NASA's Juno probe found inside Jupiter is impossible. For a long time, the story of what lies inside Jupiter looked less like a mystery and more like a settled fact. Every textbook presented a simple, elegant model, a colossal ball of gas wrapped around a small, solid core. It was a neat, tidy picture of the largest planet in our solar system, a predictable giant with clear, distinct layers, much like our own Earth. At its heart, we were taught, was a compact ball of rock and ice. But what if that entire picture, that comfortable story, is wrong? New information from NASA's Juno spacecraft has peered deep beneath Jupiter's clouds and found something at its center that didn't fit the models. Something scientists described as fuzzy, forcing a quiet revolution in how we think planets are made. The story of Jupiter, it turns out, is not a simple tale. It's one shaped by deep time, chance, and a history that is only now beginning to reveal itself. What Juno uncovered is so unexpected that it is forcing us to revise the very rules of planetary formation, reminding us that the cosmos is under no obligation to be easily understood. To appreciate how strange Juno's discovery is, we first had to travel back in time and explore the Jupiter we thought we knew. For more than a century, our vision of the gas giant's interior was built from observation, physics, and a healthy dose of educated guesswork. From the outside, Jupiter is a masterpiece of atmospheric chaos. Its surface is a tapestry of swirling cloud bands, known as zones and belts, punctuated by storms so large they could swallow the Earth whole. We have been mesmerized by this dynamic display for centuries. Scientists understood that Jupiter is made almost entirely of the two most basic elements in the universe, hydrogen and helium. Its composition is incredibly similar to the Sun, or to the primordial nebula from which our solar system was born. Jupiter, in a sense, is a cosmic relic, holding the raw ingredients of our solar system's beginning. Based on this, scientists built a logical model of what must lie beneath those clouds. It was a model of layers, defined by the immense pressure that increases as you descend. Below the visible clouds, an ocean of liquid hydrogen. Deeper still, a realm of metallic hydrogen, where the pressure is so great that hydrogen atoms are crushed, their electrons stripped away to create a sea of charged particles. This churning ocean of liquid metal is what generates Jupiter's colossal magnetic field, the most powerful of any planet in our solar system. And at the very center of it all was the anchor of the planet, the core. The consensus was clear. Jupiter must have a small, dense, solid core of heavier elements, rock, ice, and metals. This wasn't just a guess, it was a fundamental requirement of the leading theory of how planets form, known as core accretion. The core accretion model is an intuitive story that explains how planets are made from the bottom up. It starts with tiny grains of dust and ice that stick together, growing over millions of years into massive planetary embryos. For a gas giant like Jupiter, this initial core would need to reach about 10 times the mass of Earth. At that point, its gravity would become so powerful it could rapidly pull in the vast amounts of hydrogen and helium gas surrounding it. The core acted as the gravitational seed. Without it, the standard model struggled to explain how Jupiter could have formed at all. This was the Jupiter we were confident existed. A settled giant with a clear, defined structure. But science is never truly settled. While the solid core model was the accepted truth, a persistent hum of unanswered questions lingered at the edge of understanding. Our knowledge was, after all, indirect. We couldn't drill a hole into Jupiter. Every model was an inference based on its mass, its gravity, and its rapid rotation. Previous space probes like Pioneer, Voyager, and Galileo gave us tantalizing but incomplete information. The Galileo mission even dropped a probe into Jupiter's atmosphere, which survived for just under an hour before being crushed and vaporized. It sent back a wealth of data, but the picture of the deep interior remained fuzzy. Some interpretations even suggested Jupiter might not have a core at all, favoring an alternative theory called disk instability, where a giant planet could form from the direct collapse of a clump of gas and dust. The debate was fierce. Did Jupiter have a core, or not? Answering this one question would be a critical test of our fundamental understanding of how planetary systems are born. To finally solve these mysteries, a new kind of mission was needed. A probe designed specifically to peer into the heart of the giant. That probe was NASA's Juno spacecraft. And it was about to change everything. Launched in 2011, the Juno mission was named for the goddess who, in Roman mythology, could peer through the clouds her husband Jupiter used to hide his mischief. That was precisely the spacecraft's goal: to look beneath the obscuring cloud tops and reveal the planet's true nature. To do this, Juno flies in a series of long, looping polar orbits, allowing it to dive just a few thousand kilometers above the cloud tops before zipping away again. This daring path minimizes its exposure to Jupiter's lethal radiation belts while allowing its instruments an incredibly close look. Juno's primary tool for solving the core mystery is its gravity science experiment. This works by using NASA's Deep Space Network on Earth to track the spacecraft's velocity with astonishing precision. As Juno flies through Jupiter's gravitational field, even tiny variations in the mass inside the planet, like a dense core, cause minuscule changes in its speed. By measuring these changes, scientists can create an extraordinarily detailed map of Jupiter's gravity field. The planetary science community held its breath. Decades of debate were about to come to a head. As the first gravity data began to stream back to Earth, scientists prepared for a revelation. What they got was something far stranger than they could have imagined. As the data from Juno's flybys was processed, a new and baffling picture of Jupiter's interior began to emerge. Scientists were expecting one of two signatures: the sharp, distinct gravity of a compact core, or the smoother signal of a planet with no core at all. Instead, Juno found neither. What the data revealed was something completely unexpected. The core wasn't a small, dense, well-defined ball of rock and ice. But it wasn't absent, either. It was there, but it was enormous, diffuse, and indistinct. Scientists began to describe it with a new term. The core was fuzzy. Instead of a neat separation between a solid core and the metallic hydrogen above it, the boundary was blurry. The heavy elements, the rock and ice that should have been in a tight ball, were instead mixed and smeared out, blending into the metallic hydrogen. This dilute core wasn't a small feature. The data suggested this mixed region extends to nearly half of Jupiter's radius. This was a quiet bombshell. The elegant, layered diagram of Jupiter's interior was torn apart. The solid, compact core, a cornerstone of planetary theory, simply did not exist in the way we had imagined it. It was as if geologists had drilled to the center of the Earth and found not a solid iron ball, but a spongy mixture of rock and liquid extending halfway to the surface. It was a finding that immediately raised more questions than it answered. What could possibly create such a strange structure? The standard core accretion model had no explanation. The term impossible began to circulate, not because it violated physics, but because it violated every long-held assumption about how giant planets are built. The tidy king of planets was suddenly a bizarre enigma. The core was there, but it wasn't solid. It was huge, but it wasn't compact. It was a fuzzy, dilute, half-dissolved mess, and no one knew why. The discovery of Jupiter's fuzzy core left scientists with a monumental puzzle. The finding was so counterintuitive it forced a scramble for new explanations, pushing the boundaries of theoretical science. To explain it, one has to abandon the image of distinct layers, like an onion. Instead, imagine adding salt to a glass of water. At first, it's a separate solid at the bottom. But with stirring, the salt dissolves and distributes itself. Jupiter's core appears to be something analogous. The heavy elements are not sitting in a neat pile, but are at least partially dissolved and mixed into the sea of liquid metallic hydrogen that surrounds them. This led scientists to a dramatic, violent hypothesis: a giant impact. Early in the solar system's history, collisions were common. What if a young Jupiter, with a pristine and compact core, suffered a cataclysmic head-on collision with another massive planetary embryo? Simulations of such an event suggested the energy would be unimaginable, powerful enough to shatter Jupiter's original core and mix its fragments with the deep layers of metallic hydrogen. For a time, this story of ancient violence seemed to explain what Juno was seeing. However, the story of science is one of constant revision. For years, the giant impact hypothesis was the most promising explanation. But very recent work, published in 2025, has thrown this idea into doubt. A team of researchers from Durham University ran a new suite of state-of-the-art supercomputer simulations. Their results were startling. In none of their simulations did the giant impact produce a stable, dilute core like the one Juno observed. The simulations showed that while an impact does shatter the core, the heavier material would quickly resettle back toward the center, reforming a distinct, compact core. As one researcher put it, the impact shakes the planet to its core. Just not in the right way to explain the interior of Jupiter that we see today. This new research challenges, and perhaps refutes, the leading explanation. So where does that leave us? Adding another layer to the mystery, recent observations have revealed that Saturn, too, appears to have a similar, fuzzy, or dilute, core. The fact that two gas giants share this feature makes a rare, catastrophic impact less likely. It points towards a more fundamental and common process in the formation of giant planets. The truth is, we are back in a state of profound uncertainty. Juno has shown us a reality that doesn't fit our models, and the scientific community is still grappling with what it means. The fuzzy core is real. But how it got that way remains one of the biggest unsolved mysteries in planetary science. Jupiter has forced us back to the drawing board, compelling us to reconsider the very first chapter in the story of our solar system. The discovery of Jupiter's fuzzy core is more than a planetary curiosity. It's a quiet revolution that strikes at the foundation of our understanding of how planets are made. The established rulebook was the core accretion model. First, build a solid core, then, attract gas. The core had to be a massive, solid foundation to act as the gravitational seed. This model already had its difficulties, like explaining how a core could form and gather gas before the young sun's solar wind blew the gas away. But it remained the dominant theory because it seemed to explain our solar system so well. Juno's discovery of a dilute, fuzzy core presents a problem for this story. It challenges the very first step. If Jupiter's core isn't a compact object, but a huge, blended mixture, how could it have acted as the clean seed needed to start gas accretion? The finding suggests the formation process might have been a much messier affair, with solids and gas being gathered more concurrently. This breathes new life into alternative ideas, like the disk instability model, and forces all possibilities back onto the table. The implications extend far beyond Jupiter. Jupiter is our archetypal giant planet, the blueprint we use to understand the thousands of giant exoplanets found orbiting other stars. Now, that blueprint is flawed. If Jupiter, our primary example, is so fundamentally different from what we expected, what does that mean for all the other gas giants across the galaxy? The fact that Saturn also has a dilute core suggests this could be the standard way gas giants are built. The discovery forces us to confront a humbling reality. We may not know how the most common type of planet in the universe actually forms. NASA's Juno probe didn't just find a strange core, it exposed a quiet, deep gap in our most fundamental theories of creation. The rulebook for building planets has been torn up, forcing a new generation of scientists to start again, with fresh eyes. The legacy of the Juno mission is one of profound transformation. It took our simple, textbook picture of a gas giant and replaced it with a complex, mysterious, and far more interesting reality. We now know the king of planets is not a settled, layered world, but a dynamic body with a strange, fuzzy heart. But in solving one mystery, Juno has given birth to a dozen more. The central question is now one of origin. If not a giant impact, how did the fuzzy core form? Is it a primordial feature, a result of how the planet grew billions of years ago? Answering this will require a new generation of computer models, guided by the constraints Juno has provided. Is the core still evolving today, its materials continuing to dissolve and mix? The Jupiter we see may be just a snapshot in a multi-billion-year process. The discovery has also reinvigorated the study of matter under extreme conditions, a natural laboratory for physics impossible to sustain on Earth. What exotic chemistry is taking place in that vast, fuzzy core? And the implications for the rest of the cosmos are staggering. If Jupiter and Saturn both have fuzzy cores, what about the thousands of gas giants we've found orbiting distant stars? Are fuzzy cores a universal feature? Recent, more precise measurements of Jupiter's size and shape from Juno data will serve as a critical calibration standard for these exoplanet models. A better understanding of our own Jupiter directly translates to a better understanding of worlds light years away. The Juno mission is still ongoing, its orbit slowly evolving, with each pass refining our maps of Jupiter's gravity and magnetic fields. What other secrets will it uncover before its journey ends? The finding at the heart of Jupiter has ignited a fire of curiosity. It serves as a powerful reminder that the universe does not design itself to be easily interpreted. We sent a probe to confirm a story and instead, it returned a revolution. The future of planetary science is, like Jupiter's core, a little bit fuzzy. And that makes it more exciting than ever before. We are standing at the edge of a new frontier, armed with new questions, looking out at a cosmos that has suddenly become much stranger and infinitely more interesting. The journey to the heart of Jupiter has shown us that even the most familiar bodies in our sky can hold profound surprises. If this kind of calm exploration into the cosmos helps you unwind, consider liking the video and subscribing to the channel. Our exploration is just beginning, and you won't want to miss what we discover next. From a simple point of light in a telescope to a world of bewildering complexity revealed by Juno, our picture of Jupiter has been completely transformed. We've gone from the certainty of a solid core to the quiet, mind-bending reality of a fuzzy, half-dissolved heart that defies easy explanation. This single discovery has not only reshaped our view of Jupiter, but has forced us to fundamentally question the story of our own solar system's creation. The textbooks are being rewritten, not with a final answer, but with a new, more profound question. The King of Planets has humbled us, reminding us that the greatest discoveries often lie not in confirming what we know, but in revealing the vastness of what we don't. And in that mystery lies the true adventure of science. Why NASA is hunting for monsters on Jupiter's moon. There is a place in our solar system that, by all reasonable measures, should be silent. A world so cold that its surface is frozen solid, and so battered by radiation that it seems entirely inhospitable. It appears as a quiet, still marble of ice, scarred by fractures that run for thousands of miles. For a long time, it was little more than a point of light in the sky. And yet, NASA is sending one of the most complex machines ever built on a journey across nearly 2 billion miles of space to this place. Not because it is dead, but because there is a quiet, persistent suspicion that beneath this frozen facade lies something else entirely. An ocean, hidden from the sun, warmed by the pull of a giant planet. An ocean that may hold twice as much water as all of Earth's oceans combined. This is not a flight of fancy. This is the story of a real mission, a kind of cosmic detective story where the clues are written in ice, and the destination is a moon named Europa. The journey will take us miles beneath that ice, into a dark, alien abyss where sunlight has never reached. We are going there to ask a question we have always asked. Are we alone? A world of ice and fire. When Galileo Galilei first looked toward Jupiter through his telescope in 1610, he saw 4 small pinpricks of light. For centuries, they remained just that, dots in the sky, named Io, Ganymede, Callisto, and the second closest, Europa. Even through our best telescopes, Europa reveals little. It is a smooth, white world, crisscrossed with faint reddish-brown lines. In fact, it's the smoothest solid object in our solar system, almost entirely without the mountains and large craters that mark other worlds. This strange smoothness was the first clue. It hinted that the surface was young, that something was constantly repaving it, hiding its age and its history. But as our robotic explorers, the Voyager and Galileo probes, drew closer in the late 20th century, the picture slowly began to change. They revealed a world of deep contradictions. The surface temperature is a mind-numbing -260 degrees Fahrenheit, or -171 degrees Celsius. But the cold is not the greatest danger. Europa orbits deep inside Jupiter's powerful magnetic field, which traps particles and flings them at incredible speeds. The surface is caught in an invisible storm of radiation, a constant shower that would break down complex molecules and sterilize any life as we know it. A world that is both frozen and fried. Based on this, Europa should have been a low priority in the search for life. It is far outside the Sun's traditional, habitable zone, where a planet like Earth can keep liquid water on its surface. By all accounts, it should be a still, silent, and irradiated world. And yet, it is perhaps the most compelling place to look for life beyond Earth. This is the quiet paradox of Europa. The very forces that make its surface so hostile may be the same forces that power a hidden world just beneath it. The clues suggested this calm, frozen exterior was hiding something monumental. The lack of craters meant the surface was active, erasing old impacts. The strange, jumbled landscapes looked like massive icebergs that had broken apart, floated, and then frozen back into place, as if on something moving below. The long cracks looked like stress fractures on a shell being pulled by an immense force. Every piece of data seemed to point toward a single, remarkable conclusion: that this seemingly dead world was very much alive on the inside. But if the sun is too far away to warm this moon, what could possibly be strong enough to melt miles of solid ice? The answer was not in the sky above Europa, but in the colossal planet it orbits. The engine of this impossible world is Jupiter itself. Jupiter's tidal embrace. To understand how a frozen moon might hide a warm ocean, you have to forget about sunlight. The energy source here is something more raw. It's called tidal heating. We see a gentle version of this on Earth, where our moon's gravity pulls on the oceans, creating the tides. What Europa experiences is on a completely different scale. Europa is locked in a gravitational dance with Jupiter. Its orbit is not a perfect circle, but a slight oval. This means it moves closer to the giant planet, and then farther away. As it draws near, Jupiter's immense gravity stretches the entire moon. As it moves away, the pull weakens and the moon relaxes. This constant flexing, happening over and over on its 3.5-day orbit, generates an incredible amount of friction deep inside. It's like bending a paperclip back and forth. After a few moments, the metal grows warm. Now imagine that on a planetary scale. Europa is being perpetually kneaded, and that mechanical energy is turned into heat. This internal furnace is powerful enough to do something extraordinary: melt the bottom of the moon's thick ice shell, creating and maintaining a vast, global ocean. And when we say vast, the scale is difficult to comprehend. Scientists estimate the ice shell is 10 to 15 miles thick. Beneath it lies a saltwater ocean that could be 40 to 100 miles deep. For perspective, the deepest part of Earth's ocean is only about 7 miles deep. This small moon of Jupiter could hold more than twice the liquid water of all of Earth's oceans combined. This is not just a theory. We have evidence, our second set of clues. The first came from NASA's Galileo probe, which orbited Jupiter in the late 1990s. As it flew past Europa, its magnetometer detected something odd. The data hinted at something unexpected. It looked as though Europa had its own, weak magnetic field, one that changed in perfect time with Jupiter's rotation. The most elegant explanation for this is a layer of something electrically conductive inside the moon. And the most likely candidate for a planet spanning conductive fluid on an icy world is a global ocean of salty water. The magnetic field of Jupiter was creating an electrical current in Europa's hidden ocean, which in turn generated a secondary magnetic field that Galileo could detect. It was the first truly solid piece of evidence. The next clues were visual. Galileo's cameras sent back images of regions called chaos terrain, which look exactly as they sound: jumbled landscapes where massive blocks of ice have been tilted and shifted, as if they were once floating on a liquid and then froze in place. This strongly suggests a liquid or slushy layer not far below. Then there are the long lines and ridges that crisscross the moon. These are thought to be cracks in the ice shell from the tidal stress. When the shell fractures, warmer material from below could well up and refreeze, forming the ridges we see. In some images, these features have a reddish-brown color, which some believe could be salts from the ocean, mixed with other compounds and altered by radiation. The moon's surface is acting like a frozen map, pointing us toward the liquid world below. So the evidence is compelling. A massive, hidden ocean, kept liquid by the gravity of its parent planet. But water, even this much, is not enough for life. You need a recipe. And to understand if Europa has the other ingredients, we have to go deeper, into the chemistry of this dark, alien sea. The recipe for life. On Earth, the search for life has a simple mantra: follow the water. But as we've learned more about our own world, we've refined that idea. Life as we know it seems to need three things: liquid water, essential chemical elements, and a source of energy. Europa, it turns out, appears to have all three. First, water. A global ocean, dark and deep. Check. The second ingredient is chemistry. Life requires building blocks like carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. The evidence suggests Europa's ocean may have them. The story likely begins at the bottom of that ocean, on a rocky seafloor. The same tidal forces that warm the ocean also likely stir this rocky mantle, triggering geological activity. This could lead to a process called serpentinization, where seawater reacts with minerals in the rock. These reactions can release simple molecules like hydrogen and methane into the water, while also making it salty. Over billions of years, comets and asteroids would have also delivered carbon-based molecules to the surface, some of which could have made their way into the ocean. In fact, data from the James Webb Space Telescope has confirmed the presence of carbon dioxide on Europa's surface, and its location suggests it originated from the ocean below. This was the first clear sign that the ocean contains this essential element. And even older data, from the Galileo probe, is being re-examined, hinting at the presence of nitrogen-based compounds near surface fractures. So, we have water and the right chemical building blocks. That leaves the third ingredient, energy. On Earth, most life gets its energy from the sun. But beneath miles of ice, sunlight is not an option. So what could power a European ecosystem? The answer might be found in the darkest parts of our own oceans, hydrothermal vents. On Earth's seafloor, where superheated, mineral-rich water erupts from the crust, entire ecosystems thrive in total darkness. They are based on chemosynthesis, where microbes consume chemicals like hydrogen sulfide and use that energy to create food. These microbes then support strange and wonderful creatures, like giant tube worms and ghostly white crabs. Scientists believe it is highly probable that similar hydrothermal vents exist on Europa's seafloor, powered by the same tidal heating that keeps the ocean liquid. They could provide a steady source of chemical energy, a perfect cradle for life. But there's another, more exotic energy source possible, one that comes from the radiation itself. When Jupiter's radiation hits the surface ice, it can split water molecules, leaving behind oxygen and other oxidants. If this surface material can find its way down into the ocean, perhaps through a slow churning of the ice shell over thousands of years, it could provide a powerful fuel for life. The combination of oxidants from the surface and chemicals from vents on the seafloor would create a kind of planetary battery, an energy gradient that life could use. With a deep ocean, the right chemistry, and at least two potential energy sources, Europa has checked every box for habitability. The case is compelling. And now, humanity is finally sending a detective to investigate. The detective in this story is a machine, a quiet and meticulous explorer named Europa Clipper. Launched from Earth in October 2024, it is now on its long journey to the Jupiter system. Its arrival in April 2030 will begin one of the most exciting missions of planetary science ever attempted. Clipper is not designed to find life directly. Its purpose is reconnaissance. It is a robotic geologist and chemist, sent to confirm if the asterisk conditions for life truly exist. It is here to turn a world of possibilities into a world of hard data. Landing and drilling through miles of ice as hard as granite is a challenge for another time. First, we need to scout the terrain, find the most promising places, and measure the ice. That is Clipper's job. To do this without being destroyed by radiation, Clipper will perform a careful dance. It will not orbit Europa directly, which would be a fatal dose. Instead, it will enter a long, looping orbit around Jupiter. From this safer distance, it will perform 49 high-speed flybys of Europa, swooping in to gather data, and then swinging back out to safety. To perform this investigation, Clipper carries 9 scientific instruments, each designed to find a specific clue. One of the most important is an ice-penetrating radar called *reason. It will be our eyes, allowing us to see into the ice shell for the first time, to measure its thickness and search for pockets of water within it. Powerful cameras, the *ice*, will map the surface in high resolution, helping us understand the strange chaos terrains. A thermal imager, *, will scan for warm spots, which could indicate thin ice or recent eruptions. Perhaps most exciting are the instruments that will sniff the environment. There is tantalizing evidence of water vapor plumes erupting from Europa's surface. If Clipper flies through one, two instruments will spring into action. Maspex * will taste the plume, analyzing its chemistry for salts or organic molecules. Suda * will analyze any ice grains it collects. Flying through a plume would be like getting a free sample of an alien ocean. Finally, a powerful * magnetometer * will measure the induced magnetic field with far more precision than before, confirming the ocean's presence and telling us more about its depth and saltiness. The Europa Clipper mission is the culmination of decades of quiet curiosity. It is the tool we have built to solve the mystery. It will give us the most detailed picture of this world ever assembled, turning a landscape of speculation into a map of facts. And that brings us to the final question. If life is there, what could it be? The hunt for what is possible. This is where science gives way to informed, quiet speculation. What kind of life could realistically exist in a cold, dark ocean, so far from Earth? We can think about the possibilities in layers. The most probable form of life, if any exists, would be microbial. On Earth, microorganisms thrive in the most extreme environments imaginable. In Europa's ocean, it's easy to imagine a similar story. Around the hydrothermal vents we suspect are on the seafloor, chemosynthetic microbes could be flourishing, consuming chemicals for energy just as they do in our own deep oceans. Finding a single Europan microbe would be one of the most profound discoveries in history. It would mean that life is not a miracle unique to Earth, but a process that can begin in other places. If a microbial ecosystem has been stable for billions of years, could life have grown more complex? It's possible. On Earth, the jump from single-celled to multicellular life was a major step. In Europa's ocean, if the energy and resources around the vents have been plentiful, it's plausible that more complex forms could have evolved to feed on those microbes. We can look to Earth's vent communities for an analog. They are home to complex animals, giant tube worms, fields of mussels, strange shrimp, and predatory crabs. Perhaps similar organisms exist on Europa, slug-like creatures grazing on microbial mats, or filter-feeding animals anchored to the vents. Now we venture into the realm of things that fire the imagination. Is it possible for large, free-swimming predators to exist? This is highly speculative, but not outside the bounds of possibility. The key limiting factor is energy. On Earth, the evolution of large animals was powered by the rise of oxygen. If a significant amount of oxygen from Europa's irradiated surface is making its way into the ocean, it could theoretically provide the fuel needed for larger, more active life. In the absolute darkness, eyes like ours would be useless. Life would likely evolve other senses, perhaps navigating with sonar like dolphins, or by sensing the faint electrical fields of their prey. A common feature in Earth's deep sea is bioluminescence, the ability to create light. It's easy to envision a Europan ocean filled with ghostly, gliding creatures, communicating and hunting with patterns of light. Could there be large, squid-like predators with bioluminescent skin? Or fish-like organisms that navigate through senses we can't yet imagine? This is the grand, thrilling possibility. We are not just hunting for microscopic life. We are hunting for the potential of a complete ecosystem, with its own food web, its own predators and prey. The story of Europa is a testament to human curiosity. It began with a faint dot of light in a simple telescope and has led us to the edge of exploring an alien ocean. We started with a world that looked frozen and dead. But as we looked closer, the clues led us somewhere else. We found a source of internal heat, evidence of a vast hidden ocean, and the possibility of all the ingredients needed for life. Now, our robotic detective, Europa Clipper, is on its way. It will not give us the final answer, but it will provide the roadmap for what comes next. It will tell us where to look and what to look for. The hunt on Europa is about more than just finding life. It's about understanding our own origins and our place in the cosmos. For centuries, we have looked at the stars and wondered. In the dark, silent ocean of a distant moon, we may be on the verge of finding an answer. Jupiter's core is a liquid metal nightmare. For a long time, the picture of Jupiter seemed settled. We imagined a giant ball of gas with a small, solid core at its center. A colossal marble of rock and ice, lost in an endless, turbulent atmosphere. It was the image many of us grew up with, a simple, predictable heart for the king of planets. But like a fossil slowly emerging from stone, our understanding of Jupiter has changed. What has been revealed, hiding beneath those swirling clouds, is something far stranger than the simple image we held. The neat, tidy picture has been replaced by a reality of immense pressures and quiet, bizarre physics. We thought we knew Jupiter. It turns out our understanding was just beginning. What lies at its center isn't a solid object. It's a seething, conductive ocean of liquid metal, an engine that stretches the idea of what a planet can be. The story once taught in classrooms was one of two possibilities. Did Jupiter have a dense, rocky heart? Or was it gas all the way down? The answer, delivered by a spacecraft built with incredible care, was something different entirely. Data from NASA's Juno probe has revealed that the core isn't a solid object, but fuzzy and diluted, mixed into the very thing that surrounds it. And what surrounds it is an ocean of hydrogen, transformed by pressure into a liquid metal, which in turn generates a magnetic field with a moment nearly 20,000 times greater than Earth's. This finding doesn't just update a textbook. It tells a new story about how planets like Jupiter might be born, how they evolve, and what quiet strangeness can happen in the deep, crushing pressures of our solar system. The old picture, a planet we thought we knew. For most of our history, Jupiter was first a point of light, then a disk in a telescope, a world of mesmerizing bands and a single, great red spot. As our understanding grew, a model emerged, one born from a familiar logic. Planets, it was reasoned, form through accretion. Dust and gas clump together. Smaller bits form bigger bits. Eventually, a solid core emerges, a seed of rock and ice. Once that seed becomes massive enough, its gravity begins to pull in the vast amounts of gas swirling around it in the early solar system. For Jupiter, this process was spectacularly successful. It became a gas giant, a world composed almost entirely of hydrogen and helium. This story, known as core accretion, was elegant. It made sense. It predicted that deep beneath the thousands of kilometers of atmosphere, there should be a core. A dense object, perhaps 10 to 20 times the mass of the entire Earth, made of the heavy materials that started the whole process. This core would be compressed and superheated, but it would be distinct. A solid sphere at the center of a gaseous giant. This was the Jupiter of textbooks, the planet of documentaries. You could visualize it, like a stone inside a fruit. Scientists debated its exact size and composition, but the fundamental idea of a solid, well-defined core remained the leading explanation for decades. But science is a process of questioning. Some theorists proposed an alternative, the gravitational instability model, where a dense clump of the primordial gas cloud collapsed directly under its own weight, potentially without needing a solid core at all. The planet would be a more homogeneous mixture, getting denser and hotter all the way to the center. So which was it? A giant with a solid heart, or a giant with no heart at all? For a long time, there was no way to know for sure. Jupiter's immense gravity and lethal radiation belts made it an impenetrable fortress. Any machine attempting to descend would be crushed, melted, and vaporized long before it reached the center. Seeing inside Jupiter seemed impossible. To solve the mystery, humanity would need to build a messenger unlike any other. A probe that could not only survive the most hostile environment in the solar system but do so with enough grace to listen to the planet's deepest whispers. That messenger was named Juno. The game changer, an armored messenger to a hostile king. To understand the core of Jupiter, you first have to appreciate the environment a spacecraft must endure to even get close. Jupiter is not a gentle neighbor. Its primary feature is its magnetic field. Generated by the planet's rapid 10-hour rotation and its bizarre interior, this magnetic field is the largest single structure in our solar system. If you could see it from Earth, it would appear larger than the full moon in our night sky. This isn't just a bigger version of Earth's protective magnetic bubble. It's a particle accelerator. The field traps charged particles from the solar wind and, more significantly, from its own volcanic moon, Io. Jupiter's magnetosphere grabs these particles and whips them to near the speed of light, creating radiation belts thousands of times more intense than Earth's. For a spacecraft, the threat is severe. This radiation is a storm of high-energy electrons that can disrupt electronics and degrade solar panels. This is the environment that NASA's Juno spacecraft was designed to navigate. Launched in 2011, Juno is less a probe and more a scientific armored vault. Its most critical electronics are housed inside a container made of titanium. With walls about a centimeter thick, this vault acts as a radiation shield, reducing the exposure by about 800 times. It's the reason the mission can function. But even with the vault, Juno couldn't park itself in a simple orbit. The radiation is too high. So, engineers devised a brilliant flight plan. Juno executes a series of long, looping polar orbits. Each orbit takes about 53 days, and Juno spends most of that time far away from Jupiter. Then, for just a few hours, it makes a brief, precise dive. It flies in over the North Pole, passes over the cloud tops at more than 200,000 kilometers per hour, goes under the most intense radiation belts, and then flies out over the South Pole. This strategy minimizes its time in the most dangerous zones, allowing the mission to survive. As of early 2026, Juno remains operational, a testament to its careful design. Juno's primary mission wasn't to take pictures, though its camera has delivered some of the most stunning images of another world ever captured. Its main goal was to peer beneath the clouds. It does this by listening. By precisely measuring Jupiter's gravitational field, scientists can build a map of the planet's interior. As Juno orbits, tiny tugs from the planet's gravity slightly alter its path. By tracking these tiny changes, scientists can deduce how mass is distributed deep within Jupiter. Is it concentrated in a dense core? Or is it spread out? The answer, when it finally came, was stranger than either of the prevailing ideas. The descent, peeling the onion of a gas giant. Imagine you're on a journey, descending with Juno into the heart of Jupiter. This is a journey through layers of increasing pressure, where the rules of physics are pushed to their limits. We begin at what we call the surface, the altitude where the atmospheric pressure is equal to sea level on Earth. Here, temperatures are a frigid -108 degrees Celsius. This is the realm of the visible clouds. The highest layer is a haze of bright white clouds made of ammonia ice, swirling in jet streams that move at hundreds of kilometers per hour. Descend deeper, and you enter a layer of clouds thought to be made of ammonium hydrosulfide, likely the source of the planet's tan and brownish colors. Go deeper still, and you reach the third predicted cloud layer, one made of water ice and vapor, much like the clouds on Earth. But the pressure is mounting rapidly, and the temperature is rising, a consequence of the immense internal heat Jupiter radiates into space. As we continue our descent, we leave the familiar behind. We sink past the deepest clouds, into a vast, clear, but unimaginably dense atmosphere of hydrogen and helium. At a depth of about 1,000 kilometers, we cross a quiet, bizarre threshold. Here, the pressure and temperature are so high that hydrogen enters a state known as a supercritical fluid. This is a state of matter that blurs the line between liquid and gas. The boundary between the two vanishes. There is no surface. There is no boiling. There is only a single, unified fluid that has the density of a liquid but flows like a gas. This is the state of most of Jupiter's interior. From here on down, for thousands of kilometers, we are sinking through a bottomless ocean of supercritical hydrogen and helium. There is no surface to splash into. It's a gradual, seamless transition from a gas into a fluid so dense it's hard to comprehend. And as we sink deeper into this strange, featureless ocean, the pressure continues its inexorable climb, preparing to do something quietly transformative to the very atoms of hydrogen itself. The unveiling, an ocean of liquid metal. We are now thousands of kilometers beneath the cloud tops. The pressure is measured in millions of Earth atmospheres. The temperature is thousands of degrees. Here, something fundamental begins to happen to the hydrogen that makes up 90% of the planet. Normally, hydrogen is an insulator. Its electrons are held tightly. But the pressure here is an almost unimaginable force. It becomes so great that it physically squeezes the electrons away from their protons. The atoms themselves are crushed. What was once a gas of discrete atoms becomes a chaotic, flowing, super-hot soup of free-floating protons and a sea of detached, mobile electrons. And this is the moment of transformation. When you have a sea of freely moving electrons, you no longer have an insulator. You have a conductor. You have a metal. The hydrogen has turned into a liquid metal. Deep inside Jupiter, there is a literal, planet-spanning ocean of liquid metallic hydrogen. It is as conductive as copper, but it flows like mercury. This is the largest ocean in our solar system, an ocean of liquid metal thousands of kilometers deep. This exotic state of matter, first predicted in 1935, is so extreme we have only been able to create fleeting, microscopic samples of it in laboratories on Earth. In Jupiter, there is an entire world of it. This is the new reality Juno unveiled. And it gets stranger. So, what lies at the bottom of this metallic ocean? This is where Juno delivered its biggest surprise. Based on its meticulous gravity measurements, the core is not a neat, solid ball of rock and ice. It's fuzzy, dilute. Instead of a sharp boundary, there appears to be a gradual, blended transition zone. The heavy elements of the core, the rock and ice, aren't sitting in a compact lump. They are mixed in and spread out over a vast region, potentially spanning up to half of the planet's radius. It's as if the core is blended with the metallic hydrogen above it, creating a soupy, indistinct center. The temperature here is estimated to be a staggering 20,000 Kelvin, with pressures of tens of millions of atmospheres. How did it get this way? The neat core accretion models suddenly looked incomplete. One theory is that early in its history, Jupiter suffered a cataclysmic collision with another massive planetary embryo. Such an impact could have shattered Jupiter's original core and scattered its contents. However, more recent work suggests this might not be the full story. The truth is, we don't know for sure. What we do know is that the center of Jupiter is a chaotic and messy place that defies our simple models. It is a world with a blended, indistinct core, surrounded by an endless ocean of liquid metal. And this bizarre engine has profound consequences. The consequence, a dynamo of immense scale. A flowing, conductive fluid is the recipe for a planetary dynamo. It's the same principle that generates Earth's magnetic field, where a flowing ocean of liquid iron and nickel creates the shield that makes life on the surface possible. Now, take that principle and apply it to Jupiter. Replace our liquid iron core with a vast ocean of liquid metallic hydrogen. And spin that planet once every 10 hours, the fastest rotation in the solar system. What you get is a dynamo of immense scale. The swirling motions within this liquid metal ocean generate colossal electrical currents. These currents produce the most powerful magnetic field of any planet in our solar system. The magnetic moment of Jupiter is nearly 20,000 times greater than Earth's. It is an invisible structure that dominates its entire neighborhood of space. This dynamo is what makes Jupiter's environment so extreme. The magnetic field creates a magnetosphere that stretches millions of kilometers toward the Sun and extends out so far in the other direction that it sweeps past the orbit of Saturn. Inside this magnetosphere are the radiation belts. The radiation dose near the moon Europa is so high it would be lethal to a human in a matter of hours. For a shielded spacecraft like Juno, the total radiation over its primary mission is equivalent to over 100 million dental X-rays. The particles trapped in these belts are accelerated to such incredible speeds that they emit a powerful radio signal. It was the detection of these radio waves in the 1950s that first clued scientists into Jupiter's immense magnetic field. Jupiter broadcasts in the radio spectrum, a constant signal of the forces at work within. The cosmic light show and its unseen influence. The power of Jupiter's magnetic field also produces one of the most spectacular sights in the solar system. Just as Earth has the northern and southern lights, Jupiter has auroras. But here, the scale is almost incomprehensible. Jupiter's auroras are hundreds of times more energetic than Earth's, and they never stop. They are a permanent fixture, each one a shimmering curtain of light larger than our entire planet. On Earth, auroras are primarily triggered by the solar wind. But Jupiter's auroras are mainly internally driven, powered by particles from the volcanic moon Io, which are then captured by the magnetosphere. As these particles rain down, they create a constant, brilliant light show. It's a beautiful, direct manifestation of the dynamo churning deep below. You are literally seeing the power of the metallic hydrogen ocean, painted across the polar skies. The influence of this magnetic behemoth extends far beyond auroras. It fundamentally shapes the environment of its moons. The four large Galilean moons, Io, Europa, Ganymede, and Callisto, all orbit deep within this punishing magnetic field. Io, the innermost, is a world shaped by this interaction. A powerful electrical current flows between Io and Jupiter, helping to drive its extreme volcanism. Its volcanoes, in turn, spew the very material that feeds the radiation belts, creating a powerful feedback loop. Next out is Europa, a compelling target in the search for life. Beneath its icy shell, there is strong evidence for a global, liquid water ocean. But this potential cradle for life exists in a bath of lethal radiation. Jupiter's magnetic field is both a creator of complex environments and a sterilizing agent. Even Ganymede, the largest moon in the solar system, generates its own small magnetic field. But this field is utterly dwarfed by Jupiter's, creating a complex interaction, a magnetosphere within a magnetosphere. This generates its own auroras on Ganymede, a faint echo of the lights on its parent planet. The heart of Jupiter, that fuzzy, metallic core, reaches out and touches every world in its system. So what? Why this matters? So, we've journeyed to the heart of a giant. We've found a diluted core blended into an ocean of liquid metal, powering a magnetic field that shapes its entire system. It's a fascinating, complex picture. But why does it matter? First, it forces us to reconsider how giant planets are made. The simple core accretion model may be too simple. The discovery of a fuzzy core on both Jupiter and Saturn suggests the formation process is far messier than we thought. Understanding which story is true is critical, because Jupiter is our benchmark for a gas giant. When astronomers discovered Jupiter-sized planets orbiting other stars, they use our Jupiter as the primary model. If our model was incomplete, then our understanding of all those other worlds might be as well. Furthermore, the study of Jupiter's dynamo offers a window into a process that is fundamental to the habitability of planets. The dynamo inside Earth generates the magnetic field that protects us. Jupiter provides a laboratory to study this process on an extreme scale. By understanding how its metallic hydrogen dynamo works, we gain deeper insight into the magnetic shields of all planets, including our own. Ultimately, the story of Jupiter's core is a story about how science works. We build models to make sense of the universe, but we must always be ready to revise them in the face of new evidence. Like hallucigenia*, the strange Cambrian animal that was first reconstructed upside down, our understanding of Jupiter was incomplete. The planet did not change. Our understanding did. It took a dedicated, brilliantly engineered mission to finally reveal the complex truth within. We began with a simple picture, a ball of gas around a solid core. We end with something quietly strange, a world without a true surface, where the atmosphere seamlessly thickens into a supercritical fluid before pressure forges the most abundant element in the universe into a flowing, liquid metal. At its center, not a solid anchor, but a fuzzy, burning hot heart of rock and ice, blended into the metallic sea. This is the real Jupiter. A planet-sized generator, whose strange metallic core powers a magnetic field of immense proportions, creating lethal radiation belts and cosmic light shows larger than our own world. It is a world of impossible materials and physics pushed to its breaking point. For all that we've learned from Juno's daring mission, the journey is far from over. The fuzzy core raises more questions than it answers. We still don't have a clear story of how a planet like this gets created. And that, in the end, is what makes Jupiter so compelling. It's a reminder that our solar system is not a tame, predictable place. It is wild, extreme, and filled with wonders that are stranger than we can possibly imagine. The King of the Planets has revealed its heart, and it is a beautiful, complex, and unexpected world. If this kind of calm exploration into our solar system helps you unwind, consider liking the video and subscribing to the channel. And for another journey into the extreme, perhaps you'll enjoy our look at black holes next. The strangest sea in the solar system is made of metal. Sometimes, the labels we use for convenience, the simple names we give to immense things, hide a reality far stranger than we imagine. The largest planet in our solar system is called a gas giant. But that name, while helpful, is like a shadow of the real thing, a description that masks a world more complex and transformative than a simple ball of gas. And because of this, the largest ocean in our solar system isn't made of water. It's a deep, churning sea of liquid metal. Deep inside Jupiter, under pressures so great they are difficult to truly comprehend, gravity has forged this ocean from the lightest element in the universe, hydrogen. This isn't a theoretical place. It is a real, planet-spanning sea, spinning at incredible speeds. And in its movement, it powers a magnetic shield so vast, it stands as the largest single structure in our solar system. So, what is it like inside this strange ocean? What quiet forces could change hydrogen into a flowing metal? And what has this hidden world revealed to us, through the patient eyes of our robotic explorer, the Juno spacecraft? The answers are slowly refining everything we thought we knew about how giant planets are born and how they work. Prepare for a quiet journey downward, into the heart of the King of Planets, to a place where the familiar rules of matter are gently pushed to their limits. The giant we thought we knew. To the human eye, and to our first robotic visitors, Jupiter is a work of celestial art. It is a globe of swirling, graceful chaos, painted in bands of cream, rust, and ochre. Its visible surface is a tapestry of storms, the most famous being the Great Red Spot, an anticyclone so vast it could swallow the Earth, a tempest that has been observed for centuries. It is, without question, the titan of our solar system. If you were to gather all the other planets and place them on a cosmic scale, Jupiter would still be more than twice as massive as all of them combined. It is a gravitational anchor, a shepherd of asteroids, and a miniature solar system with its own family of moons. This enormous scale is why the label gas giant was created. Jupiter's composition is, after all, very similar to a star, made mostly of hydrogen and helium. When the solar system was young, gravity quietly drew this primordial gas and dust together. Jupiter gathered most of the material left over after the Sun's formation. Had it grown just a little larger, it might have ignited nuclear fusion and become a second star in our sky. For decades, this gas giant model shaped our understanding. We pictured a planet that was, in essence, a bottomless atmosphere. Our early probes, like Pioneer and Voyager in the 1970s, gave us spectacular images of the cloud tops as they flew past. They confirmed the planet's composition, measured the powerful winds, and gave us our first sense of a strong magnetic field. They showed us an upper atmosphere of unbelievably cold temperatures, where ammonia gas freezes into delicate ice clouds. These missions were monumental. They painted a portrait of Jupiter's face, but they could only hint at the nature of its heart. The name, gas giant, implies a continuous gaseous state, perhaps growing denser and denser until you reach a small, solid core. But this simple picture is misleading. It's like describing Earth as a rocky planet, without ever mentioning its oceans, its atmosphere, or its molten core. The term fails to capture the radical transformations that happen inside Jupiter. The truth is, the gaseous part of Jupiter is just a thin skin. The real Jupiter, the one hidden beneath the clouds, is not a gas giant. It is a liquid planet. And the journey from its familiar surface to its mysterious depths is a descent into a physical realm more alien than we could have imagined. The Great Descent, a journey through the impossible. Imagine a vessel, built of materials beyond our current technology, designed to withstand the unimaginable. Our mission is to descend through Jupiter's layers, to gently peel them back one by one and witness the transformation of matter firsthand. Our journey begins at the top of the clouds. This is the surface of Jupiter in the only sense that matters. A boundary defined not by solid ground, but by a level of atmospheric pressure similar to sea level on Earth. From here, we begin to sink downward. The first few hundred kilometers are a slow passage through layers of atmospheric haze. We move through the upper veils of white ammonia clouds, then deeper into brownish clouds of ammonium hydrosulfide, and deeper still, into thick, dense clouds of water ice and vapor. The temperature, once frigid, begins to rise steadily. The pressure builds, not in a linear way, but compounding with every meter we descend. Soon, we cross a quiet threshold. The distinction between gas and liquid begins to dissolve. On Earth, if you heat water, it boils and becomes a gas. There is a clear phase transition. But here, under the immense and growing pressure, that doesn't happen. Hydrogen and helium enter a state known as a supercritical fluid, a strange, fourth state of matter that is neither truly a gas nor truly a liquid. It has the density of a liquid but can flow and fill space like a gas. Imagine sinking through a fog that slowly, imperceptibly, becomes as heavy as water, and then even denser, all without a single splash, without ever crossing a visible surface. We are falling through an invisible, scalding ocean of hydrogen and helium. We continue our descent. We are now thousands of kilometers below the cloud tops. The pressure is hundreds of thousands of times greater than on Earth's surface. The temperature has risen to thousands of degrees, hotter than molten lava, yet nothing is boiling. The pressure holds the atoms together, preventing them from flying apart. Down, down we go, through this murky, super-dense fluid. Around 10,000 kilometers deep, we enter what can truly be called an ocean. We are in a vast, global sea of liquid molecular hydrogen. This is the largest ocean in our solar system, so vast it could swallow our entire planet several times over. And yet, this colossal ocean is only a prelude. It is the calm surface water above a far stranger abyss. To understand what happens next, we have to recalibrate our sense of pressure. The pressure at the deepest point in Earth's oceans is about 1,000 times that of our atmosphere. On our journey into Jupiter, that's a pressure we passed in the upper atmosphere without noticing. We are now heading for pressures of millions of atmospheres. That kind of pressure doesn't just squeeze things. It rewrites the rules of chemistry. It forces atoms into configurations that are impossible anywhere on Earth. Under this kind of quiet, cataclysmic force, the very structure of the hydrogen atom is about to be undone. The hydrogen in this deep ocean is being compressed so completely that something has to give. And what gives is the fundamental bond that defines what an atom is. We are approaching the shore of the strangest sea in the solar system. The big reveal, the ocean of liquid metal. As we continue our descent, reaching about halfway to the planet's center, the conditions become extreme. We are now 20,000 to 25,000 kilometers deep. The pressure has climbed to over 2 million times that of Earth's atmosphere, and the temperature is thought to reach as high as 15,000 Kelvin, hotter than the surface of our Sun. Here, the gradual transition gives way to the most profound transformation of all. A hydrogen atom, as we know it, is a single proton with a single electron orbiting it. In the ocean above, pairs of these atoms were still bonded together. But under this new, astronomical pressure, that simple structure can no longer hold. The atoms are pressed so near to one another that their individual boundaries begin to dissolve. The electrons are gently liberated from their protons, no longer belonging to any single nucleus. The once orderly arrangement breaks down into a flowing soup of positively charged protons, all suspended within a swirling fluid of free-moving electrons. This is the state known as liquid metallic hydrogen. It is called a metal because it can conduct electricity, an ability that comes from having electrons that are free to move. In a copper wire, electrons flow between copper atoms, carrying a current. Here, deep inside Jupiter, the same principle applies, but on a planetary scale. The hydrogen has been transformed into a perfect electrical conductor. It would flow like a liquid, but conduct electricity like a metal. This is a hot, incredibly dense, churning ocean of liquid metal. We are now swimming in the most abundant form of matter on the planet. This is Jupiter's engine room. This bizarre substance was first predicted back in the 1930s, a quiet idea born from the early understanding of quantum mechanics. But for decades, it remained purely theoretical. That has changed. In laboratories on Earth, scientists began a patient race to recreate these conditions, even if just for a moment. Using devices called diamond anvil cells, they squeeze a microscopic sample of hydrogen between two flawless diamonds. These experiments, pushing the limits of material science, have succeeded. They have created tiny, short-lived samples of hydrogen at immense pressures, and have watched it take on the properties of a metal. While these experiments can only produce a speck that vanishes in an instant, Jupiter sustains an ocean of it. This ocean is not pure hydrogen. As we descend, other elements appear. Helium, mixed in the upper layers, is believed to separate at these pressures and rain down through the metallic hydrogen. And deeper still, as we approach the core, the Juno mission has revealed a stranger brew. Elements like carbon, nitrogen, and oxygen may dissolve into this metallic sea, forming bizarre compounds that challenge our understanding of chemistry. The strangest sea in the solar system is also a chemical laboratory unlike any other. A planet-sized engine. And so, deep inside Jupiter, is an ocean of liquid metal. It is a quiet, fundamental fact of the planet. But what does it do? Why is its presence so important? The answer is that this ocean is not still. It is a dynamic, churning engine, and its work is to generate the most powerful magnetic field in our solar system. The mechanism is called a planetary dynamo. To create one, you need three things. First, a fluid that can conduct electricity. Second, a source of energy to make that fluid move. And third, you need rotation. Jupiter has all three in abundance. The conductive fluid is the vast ocean of liquid metallic hydrogen. The energy source is heat. Jupiter's interior is incredibly hot, radiating more heat into space than it receives from the Sun. This causes the metallic hydrogen to churn, as hotter fluid rises and cooler fluid sinks. And finally, there is rotation. Jupiter is the fastest spinning planet in our solar system, completing a full turn in under 10 hours. When you combine these three elements, something remarkable happens. The rapid rotation organizes the churning motions of the conductive metal into powerful electrical currents. And as the laws of physics tell us, a moving electrical current generates a magnetic field. Because this is all happening on a planetary scale, the resulting magnetic field is simply colossal. The spinning sea of metal transforms the entire planet into a gigantic electromagnet. The scale of Jupiter's magnetic field is difficult to hold in the mind. It is, by far, the largest planetary structure in our solar system. If our eyes could see it, it would appear several times larger than the full moon in our night sky. Its tail stretches for millions of kilometers, extending beyond the orbit of Saturn. This magnetic bubble is, in places, nearly 20,000 times stronger than Earth's, and it traps a ring of intensely energetic particles, creating radiation belts that are incredibly powerful. This dynamo powers spectacular auroras at Jupiter's poles, light shows far grander than our own. And as our understanding has grown sharper, through NASA's Juno spacecraft, a new layer of detail has emerged. Its measurements have revealed that the dynamo is happening closer to the planet's surface than we thought. The field is also strangely asymmetrical, with complex features concentrated in the northern hemisphere. This suggests the dynamo is not a simple, uniform process, but a messy, complex one. This planet-sized engine acts as a cosmic shield, deflecting the solar wind. And it all begins with that quiet transformation deep inside, the crushing of simple hydrogen into a swirling, superheated, electricity-conducting metal. The deepest mystery, the fuzzy core. For all that we have learned, the final destination of our journey remains shrouded in a quiet mystery. For decades, the story of Jupiter's formation followed a neat, tidy script. This theory proposed that a solid core of rock and ice, perhaps 10 to 15 times the mass of Earth, formed first. Once this seed grew large enough, its gravity began to pull in the immense envelope of gas that surrounds it today. It was a logical and intuitive picture, and it predicted that at the very center of Jupiter, we should find a distinct, compact core, sharply separated from the ocean above it. This was the leading story for generations. And then, our robotic emissary, the Juno spacecraft, began to tell a different story. Juno's primary mission was to map Jupiter's gravity and magnetic fields. By flying in a long, elliptical orbit, it could detect tiny variations in the planet's gravitational pull. These subtle changes revealed how mass is distributed deep inside. As the data came in, it became clear that the old model was incomplete. What Juno saw did not look like a small, solid core. There was no sharp boundary. There was no compact ball. Instead, Juno revealed what scientists now call a dilute, or fuzzy, core. It seems the heavy elements, the rock and ice, are instead mixed and smeared out, blending gradually into the metallic hydrogen over a vast region, one that might span nearly half of Jupiter's radius. This discovery didn't just add a new chapter, it suggested the story we had been telling ourselves might be wrong. A neat, gradual formation process doesn't easily explain a core that has been dissolved and spread out. The story of how this happened is still being written. One idea was that Jupiter suffered a cataclysmic collision in its youth that shattered its original core. Another, quieter theory is now gaining ground. That this dilute structure formed gradually, as rock, ice, and gas were pulled in and mixed together from the very beginning. Whatever the cause, the heart of the king of planets is not a solid stone, but a diffuse, enigmatic haze that we are only just beginning to see. Our descent is complete. We have journeyed from the familiar, swirling clouds, down through a strange ocean of supercritical fluid, and into the heart of the true Jupiter. A world-spanning sea of liquid metallic hydrogen. We have witnessed the quiet, alchemical transformation of the universe's simplest element into a flowing, conductive metal. We've seen how this strange ocean, spinning at incredible speeds, becomes a planetary dynamo, generating a magnetic shield of immense scale and power, born from the churning of a metal sea thousands of kilometers beneath the clouds. And yet, after reaching the very center, we are left not with a final answer, but with a deeper mystery. The revelation of a fuzzy core has overturned decades of theory, forcing us to rethink the story of how planets like Jupiter come to be. The heart of the giant is not a solid foundation, but a nebulous, dissolved enigma. The solar system's largest ocean, then, is made of a substance that challenges our definition of metal. It is an engine that powers forces on a scale we can barely model, and it holds clues to the birth of our own planetary family. We sent a probe to solve the riddle of Jupiter, and in return, the planet has shown us that the mysteries are deeper, stranger, and more beautiful than we ever knew. And as we continue to listen to the signals from our robotic explorer, we are reminded that in the quest to understand the cosmos, every arrival is simply the beginning of the next great voyage into the unknown. Jupiter's core isn't what we thought, and scientists are freaking out. We thought we knew Jupiter. For a long time, its story seemed written. We pointed our telescopes at the king of our solar system, the quiet giant that holds more mass than all the other planets combined. We saw its storms, its bands of clouds, its family of moons. And from all that watching, from our understanding of physics, we built a picture of what must lie at its heart. The theory was an elegant one. It was logical. Deep beneath the crushing pressures, there had to be a core. A small, dense, solid ball of rock and ice. The first seed from which everything else grew. NASA sent a quiet, armored messenger on a 5-year journey across the solar system to see it. The mission was called Juno. Its purpose was to give us the final, gentle proof that our theories about Jupiter were correct. But that is not what happened. Instead of a confirmation, Juno sent back a question. A quiet and profound mystery that has asked planetary scientists to rethink the story they were so sure of. Because deep inside Jupiter, buried beneath swirling hydrogen, its core, it isn't what we thought at all. It is not small. It is not solid. And the discovery of what it is has begun a slow and deep correction in our understanding of how planets, including our own, are born. This is a journey into that story. Not a story of a single discovery, but of how science works. Of how understanding, like an animal in deep time, slowly changes its shape. Welcome. If this kind of calm exploration into the cosmos helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. To understand why this discovery is so important, you first have to appreciate Jupiter's quiet role in our solar system. It is not just another planet. It is the gravitational anchor, a body so massive that its birth and evolution shaped the fate of everything else around it. Imagine the dawn of our solar system, 4.6 billion years ago. A vast, spinning cloud of gas and dust begins to collapse. In the swirling disk that remains, tiny dust grains stick together. And out there, in the cold expanse, one of these growing bodies gathered more and more material. This was the protoplanet Jupiter. It became the first planet to form, a gravitational gatekeeper that shaped the architecture of the entire system. Its immense pull may have shepherded water-rich materials toward the inner solar system, delivering some of the ingredients for life to planets like Earth. Jupiter is not just a part of our solar system's history, its story is our history. To understand it is to understand our own origins. Jupiter is a world of superlatives. Its diameter is 11 times that of Earth. It rotates faster than any other planet, completing a day in just under 10 hours. This rapid spin causes its atmosphere to churn into the iconic belts and zones we see, bands of clouds moving in opposite directions at hundreds of miles per hour. Within these bands are storms larger than our entire planet. The most famous, the Great Red Spot, is a cyclone that has been raging for centuries. Beneath this visible layer of ammonia clouds, the conditions become truly alien. The pressure builds relentlessly. The hydrogen that makes up most of the planet is squeezed so intensely that it transitions from a gas into a bizarre liquid. Deeper still, the pressure becomes millions of times greater than on Earth's surface. Here, the hydrogen is crushed into something that doesn't exist anywhere else in our solar system: a sea of liquid metallic hydrogen. This swirling, metallic ocean, larger than the Earth itself, is what generates Jupiter's colossal magnetic field. For decades, this was the picture we had. An outer layer of gas, a vast ocean of liquid metallic hydrogen, and at the very center, the final piece, the core. Understanding this core was the ultimate goal, the key to unlocking Jupiter's formation story. But you can't see it. You can't drill to it. You can only probe it indirectly, by listening for the faintest of whispers from the planet's deep interior. And to do that, you need a very special kind of messenger. Before we can appreciate the quiet surprise of Juno's discovery, we have to travel back to the world of planetary science before *2016. In that world, an elegant idea called the core accretion model was the leading story of how giant planets form. Imagine a tiny seed of rock and ice, perhaps 10 to 15 times the mass of Earth, forming in the early solar nebula. As it grows, its gravity becomes powerful enough to start pulling in the vast amounts of gas surrounding it. This begins a runaway process. The more gas it gathers, the more massive it becomes, and the more powerful its gravity gets. In a relatively short time, this tiny solid seed cloaks itself in an atmosphere hundreds of times more massive than the core itself. This model was compelling for a reason. It explained so much. It provided a neat sequence of events. And most importantly, it gave us a clear, testable prediction. If the core accretion model was correct, then at the very heart of Jupiter, there should be a distinct, compact core. Think of it like a piece of fruit. You have the skin, the atmosphere, the fleshy part, the metallic hydrogen, and right in the middle, a hard, solid pit. That pit was what we were looking for. Of course, science is never without a healthy debate. A competing theory, known as gravitational instability, proposed a more direct formation. In this scenario, there was no solid seed. Instead, a dense region within the solar nebula itself became unstable and collapsed under its own gravity. If this were the case, Jupiter might not have a distinct core at all. So, for decades, the question was simple. Was there a core, or was there not? The truth was, from our distant vantage point, we were making educated guesses. The only way to settle the debate was to go there. We needed to send a probe that could fly closer than ever before, brave the radiation, and listen to the gravitational heartbeat of Jupiter itself. We needed Juno. In Roman mythology, the god Jupiter was said to shroud himself in a veil of clouds. Only his wife, the goddess Juno, could peer through them and see his true nature. It is the most fitting name NASA could have chosen. Launched on August 5, 2011, the Juno spacecraft began a 5-year journey to our solar system's largest planet. Jupiter's magnetic field traps particles from the Sun, creating radiation belts thousands of times more intense than Earth's. For a normal spacecraft, this environment would be overwhelming. Juno had to be built like an armored vault. At its heart is a cube of titanium, a suit of armor protecting the sensitive electronics. But even this armor wouldn't be enough for prolonged exposure. So, mission planners devised a brilliant, careful orbit. Instead of circling the equator, Juno was placed in a vast, elliptical polar orbit. For most of its 53-day journey, it stays far away. But once per orbit, it performs a perijove pass. It dives in, skimming just 4,200 kilometers above the cloud tops, flying through a narrow gap between the planet and its inner radiation belt, before heading back out into the safety of space. For a few hours, all of Juno's instruments are on, gathering as much data as they can. To find the core, Juno uses its gravity science instrument. This instrument is the spacecraft itself. As Juno flies over Jupiter, its path is subtly affected by the planet's gravity. If it flies over a region that is slightly denser, like a compact core, it receives a tiny gravitational tug, changing its speed by millimeters per second. This alters the frequency of the radio signal Juno beams back to Earth, a phenomenon known as the Doppler effect. By measuring these tiny shifts, scientists can create a map of Jupiter's gravity. It's like rolling a marble over a thick mattress to feel for a heavy object hidden underneath. You can't see the object, but you can map its location by watching how the marble's path dips and rises. On July 4, 2016, Juno successfully entered its orbit. The science team was ready to receive the data that would finally reveal the neat, tidy core they had been expecting. The first signals came back. And then, a quiet realization. The signal wasn't right. It wasn't what anyone expected. Back on Earth, the data from Juno's gravity experiments began to paint a picture. The science team was looking for a specific signature, a sharp, strong gravitational tug over the planet's center. But the signature wasn't there. Instead, the gravitational influence was spread out. It was diffuse. The data suggested the heavy elements at Jupiter's center were not packed into a neat ball. They were mixed in with the hydrogen, spread out over a vast region. The sharp spike of gravity they expected was replaced by a broad, gentle hill. There was no clear boundary. The core, if you could even call it that, was fuzzy. This was the moment that changed things. The models of Jupiter's interior, so carefully constructed, were suddenly incomplete. The data showed that the central region of Jupiter is a massive, sprawling zone where heavy elements are dissolved and mixed into the deep metallic hydrogen. This dilute core isn't small. It extends out from the planet's center to nearly half of Jupiter's radius. It contains between 10 and a few tens of Earth masses of heavy material. But this material is not a solid object. It's a gradient. Imagine dissolving sugar in water. The standard model expected all the sugar to be a solid lump at the bottom. What Juno found was more like a gradient, where the water is sweetest at the bottom and gradually becomes less so as you move up. There's no sharp line where the sugar water ends and the pure water begins. This is Jupiter's core. A vast, churning region where the concentration of rock and ice is highest at the very center and gradually feathers out. This slow correction tells an important story, not just about Jupiter, but about how science works. The discovery posed a monumental question. How does a planet get a core like this? If it wasn't formed this way, then something must have happened to it. The neat and tidy story of planetary formation had just been torn apart, and in its place was a quiet, cosmic mystery. The discovery of the fuzzy core sent scientists looking for a new story. One dramatic possibility emerged: a giant impact. The theory goes like this. Early in Jupiter's history, not long after its formation, another massive object, a protoplanet perhaps as massive as 10 Earths, slammed into it. The energy released would have been almost incomprehensible. The impact could have shattered Jupiter's original, compact core, mixing the debris with the deep hydrogen envelope. The planet would have been shaken to its very center. This idea made a certain kind of sense. We see evidence of giant impacts elsewhere, like in the formation of our own moon. However, the story of science is one of constant refinement. In late 2025, new research cast doubt on this scenario. Scientists at Durham University used powerful simulations to model these collisions. The results were clear and unexpected. None of the simulations produced a stable, fuzzy core like the one Juno observed. According to the new models, even after such an impact, gravity would quickly cause the heavier material to settle back down, reforming a more compact core. As Dr. Thomas Sandnes, the lead author, noted, the impact shakes the planet, just not in the right way to explain the interior of Jupiter that we see today. So, if a giant impact didn't create the fuzzy core, what did? The same research has propelled a quieter idea to the forefront: that Jupiter's fuzzy core isn't the result of a single, violent event, but a more gradual process of formation. This line of thinking suggests that Jupiter's core was never a solid object to begin with. Instead, as the planet grew, it may have slowly absorbed a mix of both pebbles of rock and ice and hydrogen gas. Under the extreme pressures and temperatures deep inside, these materials may not have separated neatly. The rock and ice might have dissolved directly into the hydrogen, creating a dilute, messy mixture from the very beginning. What makes this gradual formation theory so compelling is that we're now seeing evidence for it elsewhere. Observations of Saturn also suggest it has a similar fuzzy core. The odds of two planets having their cores shattered by rare, giant impacts seems unlikely. But if fuzzy cores are a natural outcome of the planet formation process itself, it makes sense that both Jupiter and Saturn would share this feature. It suggests that giant planets all across the universe might have messy, complex interiors. The story of Jupiter's core is a perfect example of the scientific process. We started with an elegant theory. We sent a messenger to confirm it. The messenger sent back data that told a different story. This led us to a dramatic new idea, and now, even newer work is pushing us toward a more fundamental rethinking of how giant planets are built from the ground up. Each revelation has only led to deeper questions. Juno's mission has continued its work past September 2025, and with each orbit, the data continues to refine our understanding. Very recent findings from early 2026 used Juno's radio signals to remeasure the precise shape of Jupiter. These tiny adjustments, just a few kilometers off previous estimates, are crucial. As one scientist noted, these few kilometers matter, because they help constrain what can be happening deep inside. It's a reminder of how science works: a slow, careful convergence on a better explanation. The discovery of Jupiter's fuzzy core has replaced a simple picture with one that is complex, dynamic, and born of processes we are only just beginning to understand. It tells us that the universe is often quieter and stranger than our models predict. The Juno mission was sent to confirm what we thought we knew. Instead, it revealed how much we still have to learn. It solved one question only to create a dozen more. These are the questions that drive science forward, the puzzles that inspire us to keep exploring. The data from Juno continues to pour in. We may not have the final answer yet, but we have a far more interesting picture than we ever imagined. The heart of the giant is not a simple, solid pit. It is a vast, dynamic realm where the lines are blurred, a testament to a history more complex and mysterious than we ever dreamed. And as we continue to listen to the whispers from deep inside Jupiter, we are not just learning about one planet. We are learning about the very recipe for creating worlds. We found an alien ocean hiding at Jupiter. Sometimes, the most profound discoveries aren't found in distant galaxies or in faint signals from faraway stars. Sometimes, they're waiting quietly, right in our own cosmic backyard. What if the most likely place to find alien life has been hiding somewhere we thought was impossible? A place so cold, it should be frozen solid. A place of deep mystery and quiet beauty. For decades, we've pointed our instruments outward, listening for a message from the void. But the whole time, perhaps the greatest secret in the solar system was locked away, just next door. Then, scientists found it. Overwhelming evidence of a vast, salty ocean, hidden where it shouldn't exist. Not on Mars, not on Venus, but beneath the fractured, icy shell of one of Jupiter's moons. A world called Europa. The discovery was so quiet, and yet so monumental, it has completely reshaped our search for life beyond Earth. Now, the question is no longer if water is there. We know it is. The question that keeps scientists awake at night, the question that's now driving missions across the solar system is something living in it? This is not just a story about a moon. It's the story of a revelation that has rippled through science, asking us to reconsider everything we thought we knew about where life can exist. It's a detective story that began with grainy images and faint magnetic whispers. And it's leading us toward an answer to the oldest question we've ever asked. Are we alone? The answer might be waiting for us, swimming in the dark, silent oceans of Jupiter. The mysterious moon. Before we could even dream of an ocean, Europa was an enigma. When the Voyager spacecraft first flew past in 1979, they sent back images of something unfamiliar. Our own moon is a landscape of ancient craters, a static museum of cosmic history. But Europa was different. It was strikingly smooth, a quiet, white and yellow sphere, streaked with deep, reddish-brown lines that ran for thousands of kilometers across its surface. It was the lack of features that was so puzzling. A world in the Jupiter system, a crossroads for comets and asteroids, should be covered in scars. But Europa looked young, almost pristine. Its surface was telling a story of constant renewal. Something was erasing the craters, paving over the pockmarks of history with fresh, clean ice. It was as if the moon had a quiet geological heartbeat, a process that kept it looking new. And then there were those strange streaks. Known as lineae, they crisscross the moon's face like a network of veins. Some look as if the world had been fractured, and then healed itself, with some dark material welling up from below. For decades, these features were a mystery. What could create such a pattern? What was this reddish stain on the ice? The early images were just a glimpse, a look into a world that defied easy explanation. The smoothness suggested a young surface. The lines suggested a dynamic world beneath. And the whole picture hinted at a source of energy that shouldn't be there. Located more than 5 times farther from the Sun than we are, Europa receives almost no warmth. Its surface temperature drops to a mind-numbing -160 degrees Celsius, or -256 degrees Fahrenheit. At those temperatures, ice is as hard as granite. It shouldn't move. It shouldn't crack and heal. It should be a static, frozen, dead world. But Europa was not dead. It was whispering a secret. And to understand it, we had to get a much closer look. The trail of evidence. The next chapter belongs to a spacecraft that changed everything, Galileo. It became the first probe to orbit Jupiter, and between 1995 and 2003, it made a series of daringly close flybys of Europa. What it found was the clue that unlocked the mystery. One of Galileo's key instruments was a magnetometer, designed to measure magnetic fields. And it detected something strange. As Jupiter's powerful magnetic field washes over Europa, Galileo found that the moon was creating its own, secondary magnetic field in response. This only happens under one condition. There has to be a layer of something electrically conductive beneath the surface. Think of it like this. When you move a magnet past a copper wire, you create a current. In the same way, Jupiter's moving magnetic field was creating currents inside Europa, and those currents were generating their own magnetic field. Rock isn't a good conductor. Pure ice isn't either. But something is. A massive layer of liquid saltwater. In that moment, the paradigm shifted. The data was clear. Hiding beneath that shell of ice, there had to be an ocean. But how? How could a liquid ocean exist so far from the Sun? The answer lies in a quiet, cosmic tug-of-war. Europa orbits Jupiter in a celestial dance with two other moons, Io and Ganymede. This regular, rhythmic alignment means Europa's orbit is not a perfect circle. It's stretched into a slight ellipse. As Europa gets closer to Jupiter, the planet's immense gravity pulls on it, stretching the moon. As it moves away, the pull weakens and Europa relaxes. This constant stretching and squeezing, over and over, generates an incredible amount of friction inside the moon. It's a process called tidal heating. You can feel a simple version of it yourself. If you take a paperclip and bend it back and forth, the metal gets hot. Now, imagine that paperclip is a world the size of our moon, being bent by the largest planet in our solar system. The heat generated is immense, more than enough to melt the bottom of the ice shell and sustain a global ocean. The magnetic field told us the ocean was there, and tidal heating explained how. The case was getting stronger, but more evidence would come from a telescope back here on Earth. Using the Hubble Space Telescope, astronomers watched Europa, and they found something spectacular. On several occasions, Hubble detected what appeared to be faint plumes of water vapor, erupting from the surface and shooting hundreds of kilometers into space. They seem to be intermittent, like quiet geysers, but if they are real, they are blasting samples of the subsurface ocean directly into space. Then, a new look at that old Galileo data revealed another piece of the puzzle. A recent study, using modern techniques to re-examine data from 1997, found the first definitive signature of ammonia on Europa's surface, clustered around the major fractures in the ice. Ammonia acts like an antifreeze, and its presence there strongly implies it's coming from a liquid source below. Crucially, it's a nitrogen-bearing molecule, and nitrogen is a foundational building block for life. The evidence, collected over decades, all pointed to one stunning, inescapable conclusion. The alien ocean revealed. Beneath an ice shell, perhaps 15 to 30 kilometers thick, Europa hides a global, liquid saltwater ocean. And it is vast. Deeper than any ocean on Earth, scientists estimate this hidden sea could contain about twice as much water as all of Earth's oceans combined. A moon slightly smaller than our own holds more liquid water than our entire planet. It's a true, world-encircling ocean, sloshing in the darkness beneath a roof of solid ice. The discovery of this ocean world is one of the most important in history. It shatters our old, sun-centric view of a habitable zone. For centuries, we defined that as the narrow band around a star where a planet's surface could have liquid water. But Europa changes the rules. It proves that a world doesn't need to be close to its star to have water. The energy for life doesn't have to come from a sun. It can come from gravity itself. This idea vastly expands the number of places where life could possibly arise, not just here, but around the gas giants we are now discovering orbiting other stars. The properties of this ocean are just as exciting as its existence. The magnetic field data tells us it's salty, which means the water is in direct contact with a rocky seafloor below. For billions of years, water has been circulating, reacting with rock, becoming a complex chemical soup. This interaction is critical. On Earth, the boundary between the ocean and the seafloor is a place of incredible chemical energy and life. This transforms Europa from an icy moon into the most compelling place in our solar system to search for life. The pieces are all there. For years, astrobiologists have talked about three key ingredients for life: liquid water, essential chemical elements, and a source of energy. Europa has the water. It has the chemical elements leached from its rocky core. Recent studies even suggest a process where salty surface ice could sink through the shell, delivering fresh ingredients from the surface to the ocean below. And with the discovery of ammonia, we now have evidence for nitrogen. So what about the final ingredient? A source of energy? The sun can't reach the bottom of this deep, dark ocean. But it doesn't have to. What we are learning about Europa is forcing us to rethink the very idea of a habitable world. If this kind of calm exploration into our solar system helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. Every new piece of data brings us closer to an answer, and you won't want to miss what we find next. A world of deep-sea vents? On the floor of Earth's oceans, far from the reach of sunlight, there is a world that was completely unknown to us until 1977. Here, volcanic cracks in the planet's crust spew out superheated, mineral-rich water. These are hydrothermal vents, and they are teeming with life. Entire ecosystems thrive in total darkness, powered not by the sun but by chemical reactions. Bacteria form the base of this food chain, using the energy from chemicals in the vent water. It was a discovery that proved life doesn't need sunlight. It just needs a chemical energy source. Could a similar story be playing out right now, on the seafloor of Europa? The same tidal heating that keeps the ocean liquid could also be flexing the rocky mantle beneath it. This could power volcanic activity on the seafloor, creating hydrothermal vents just like the ones on Earth. They would be oases of warmth and nutrients in the cold, dark depths. If life exists on Europa, it's at these hypothetical vents that it most likely began, and where it could be thriving today. We may even be seeing quiet hints of this on the surface. Those mysterious reddish streaks could be salts from the ocean, brought to the surface and irradiated. It suggests a connection between the deep interior and the world above. However, some recent modeling studies suggest Europa's rocky interior might be relatively quiet today, which would limit the energy available from vents. This doesn't rule out life, but it suggests the most energy-rich places might be closer to the ice-ocean boundary, where chemistry from the surface and the ocean meet. The debate itself highlights just how much is still a mystery. But the possibility that an environment like Earth's deep-sea vents could exist on a moon of Jupiter is a powerful and motivating idea. Europa is a natural laboratory, a place where the conditions might be strikingly similar to those on primordial Earth. We have an ocean, we have the chemical building blocks, and we have a powerful way to create energy. And what's even more astounding is that Europa might not be the only one. A system of ocean worlds. The revelation of Europa's ocean opened our eyes. Scientists began to look at the other icy moons of the outer solar system and saw them in a new way. If tidal heating could happen on Europa, could it be happening elsewhere? The answer seems to be yes. Jupiter's neighborhood isn't just home to one ocean world, it's a whole system of them. First, let's travel outwards to Ganymede. Ganymede is a behemoth. It's the largest moon in our solar system, bigger than the planet Mercury. And it holds a unique distinction. It's the only moon known to generate its own magnetic field, from a churning, liquid iron core, like a planet. Just like with Europa, the Galileo spacecraft found an anomaly. Within Ganymede's own field, it detected a secondary, induced field, pointing once again to a subsurface ocean of salty water. Later, the Hubble Space Telescope confirmed it. By watching the rocking motion of Ganymede's auroras under Jupiter's influence, scientists could tell they were being dampened, just as you would expect if a global, conductive ocean was resisting the change. Ganymede's ocean is thought to be even deeper than Europa's, buried beneath a much thicker crust of ice. Unlike Europa, its ocean may not touch the rock below, but instead sit in a bizarre club sandwich structure. Ice, then water, then another layer of high-pressure ice. This could make it harder for life-giving minerals to reach the water, but the sheer scale of it is staggering. And the tour doesn't stop there. Let's swing out to the final of the 4 Galilean moons, Callisto. Callisto is the quiet one. Its surface is ancient and covered in craters, telling a story of geological calm. For a long time, it was considered a dead world. But even here, Galileo's magnetometer picked up the faint whisper of an induced magnetic field. The data suggests that even this ancient moon likely harbors a salty ocean deep beneath its crust, kept liquid perhaps by leftover heat and a high concentration of salts like ammonia. In just a few decades, our view of Jupiter's system has been revolutionized. We've gone from thinking of it as a gas giant with a retinue of dead, icy rocks to understanding it as a miniature solar system of ocean worlds. 3 moons, 3 hidden oceans, 3 distinct possibilities for life. The question was no longer theoretical. It was time to go back. The hunt begins. Knowing the oceans are there is one thing. But to hear what they have to say, we need to send a dedicated laboratory across the solar system. And that is what we are doing. 2 of the most ambitious missions in history are, as we speak, quietly hurtling towards Jupiter. First is NASA's flagship mission, the Europa Clipper, launched in October 2024. Its primary goal is fundamental: to characterize Europa's habitability. It is a reconnaissance mission of the highest order. After a long journey, Europa Clipper will arrive at Jupiter in April 2030. It will make nearly 50 breathtakingly close flybys of Europa, some just 25 kilometers above the ice. Its powerful ice-penetrating radar will be the first instrument to peer directly through the shell, to map its thickness and try to get the first direct sense of the ocean below. Other instruments will sample any material on the surface or, if we're lucky, flying through a plume, sniffing the ice for the chemical signatures of biological processes. Joining the journey is the European Space Agency's JUICE mission. Launched in April 2023, it will arrive at Jupiter in July 2031. While its primary target is the giant moon Ganymede, it will also perform crucial flybys of Europa and Callisto, giving us a comparative study of these worlds. As of early 2026, both missions are performing well on their long cruises through the solar system. Together, they represent a monumental effort by humanity to step into the outer solar system and listen. We stand at a quiet, remarkable moment in history. The grainy photos from Voyager sparked a mystery. The magnetic data from Galileo gave us a revelation. And now, the advanced explorers, Europa Clipper and JUICE, are on their way to listen to the next chapter. For millennia, the question, "Are we alone?" has been a thought experiment. But the discovery of Europa's hidden ocean, and the oceans of its neighbors, has brought that question into the realm of testable science. We have found a potential habitat, not in some distant, unreachable star system, but here, in our own solar system. A place we can actually go. If we find evidence of life, even simple microbial life, it would mean the spark of biology is not a unique fluke that happened only on Earth. It would mean the universe is likely teeming with it. And if we find nothing? If Europa's ocean is sterile and lifeless? That, too, would be a profound discovery. It would tell us that even with all the right ingredients, life is perhaps a much rarer and more precious thing than we imagined. Either way, we are on the cusp of an answer. In the early 2030s, data will begin to stream back. Every radar scan, every magnetic measurement, every particle of dust will be a clue. The journey has been long, from a faint point of light in a telescope, to a mysterious streaked world in a camera, to the precipice of discovering a second Genesis. The great, dark, silent ocean of Europa is waiting. And soon, for the first time, we will be ready to listen to the secrets it has to tell. The real reason we're racing back to Jupiter's moon. Far from the sun, in the quiet gravitational hold of a gas giant, a small moon is moving. From a distance, it appears unremarkable. A pale, marbled sphere wrapped in a shell of ice so cold it behaves like rock. It looks like a still, silent, and ultimately, a dead world. But it's not. A closer look reveals something else entirely. Something is bleeding through the ice. Vast, reddish-brown stains stretch for thousands of kilometers across its surface, like a quiet wound. These aren't random cracks, they're clues. They are evidence of a hidden world, buried miles beneath the frozen crust, a vast, dark, global ocean with more water than all of Earth's oceans combined. For a long time, this was an idea, a compelling theory. Now, it's a near certainty. And this certainty has started a new kind of race. Not a race between nations, but a quiet race for understanding. We are sending our most advanced robotic explorers on a journey of almost 2 billion miles, back to this distant moon, for one profound reason: to learn what, exactly, is making that stain. The answer could be simple salts, changed by Jupiter's fierce radiation. Or it could be something more. It could be the chemical signature of a living ocean. It could be the first real evidence that we are not alone in the universe. The anomaly of the ageless ice. To understand why this moon, Europa, has become the most compelling place in the search for life beyond Earth, we have to go back to the first images that left scientists quietly bewildered. When NASA's Voyager spacecraft passed the Jupiter system in 1979, they sent back our first close portraits of its moons. Io was a volcanic nightmare. Ganymede and Callisto were ancient and heavily cratered, their surfaces old battlegrounds, bearing the scars of billions of years of impacts. But Europa was different. It was smooth, eerily smooth. In fact, it's the smoothest known object in the entire solar system. It lacked the deep, ancient craters that should have marked its surface after 4.5 billion years of cosmic history. A world without craters is like a story without a past. It means the surface is being actively renewed. Scientists realized they were looking at an incredibly young surface, perhaps only tens of millions of years old. Something was gently erasing history. Then, as the images grew clearer with the arrival of the Galileo spacecraft in the 1990s, the mystery deepened. The surface wasn't just smooth, it was a chaotic, fractured puzzle. Enormous cracks, called lineae, crossed the entire globe. And in many places, the ice sheet looked as if it had been shattered into enormous rafts, which then drifted apart and froze back into place at strange angles. These areas were called, fittingly, chaos terrain. It was as if giant pieces of the crust had broken free, floated on something liquid below, and then refrozen in a jumbled mess. This was the central puzzle. How could a world so far from the sun, with surface temperatures dropping from -160 degrees Celsius at the equator to -220 degrees at the poles, have a surface that looked so active? Solid ice, miles thick, doesn't just rearrange itself. This was not the behavior of a dead, frozen world. This was the behavior of a thin, brittle skin stretched over something moving beneath. And then there were the colors. The long, linear cracks were not white like the ice around them. They were a dark, reddish-brown. This material seemed to be seeping up from below, staining the surface along these fractures. For decades, scientists have debated what this could be. Early ideas suggested salts left behind after briny water erupted and froze. Another possibility was sulfur, sprayed out by Jupiter's volcanic moon, Io. The color was a puzzle, but its location was a clue. It was concentrated in the youngest parts of the surface, the cracks and chaos terrains. The very places where the interior seemed to be interacting with the outside world. A smooth surface, vast, chaotic fractures, and a mysterious, colorful stain bleeding from within. These were the symptoms of a much larger, hidden secret. To solve this puzzle, scientists had to answer a fundamental question. Where was the energy coming from to drive all this activity? The engine of a hidden ocean. For a world to be geologically active, it needs heat. On Earth, that heat comes from its formation and the decay of radioactive elements in its core. But Europa is small, only slightly smaller than our own moon. Any heat it had from its formation should have radiated away long ago. And sitting more than 5 times farther from the sun than Earth, solar energy is incredibly weak. By all conventional logic, Europa should have been frozen solid for billions of years. And yet, the evidence of its dynamic surface was undeniable. This contradiction forced scientists to look for an unconventional energy source, and they found it in the most powerful force in the neighborhood, Jupiter itself. The answer is a phenomenon called tidal heating. It's a concept that's both simple and immense. We see a gentle version of it on Earth, where the moon's gravity pulls on our oceans, creating the tides. But what's happening at Europa is on a completely different scale. Jupiter is a monster. Its gravitational pull on its moons is enormous. As Europa orbits Jupiter, this gravity constantly tugs at it, stretching and squeezing the little moon. If Europa's orbit were a perfect circle, this would eventually settle down. But Europa's orbit isn't a perfect circle. It's a slight ellipse. This is where the other moons come in, performing a delicate cosmic dance. Europa is locked in an orbital resonance with two of its neighbors, Io and Ganymede. This constant, rhythmic pulling from its neighbors prevents Europa's orbit from ever becoming circular. Because its orbit is elliptical, its distance from Jupiter constantly changes. When it's closer, the gravitational pull is stronger, and the moon is stretched out more. When it's farther away, the pull is weaker, and the moon relaxes. This constant flexing generates an incredible amount of friction deep within Europa's interior. Think of bending a metal paperclip back and forth. Keep doing it, and the metal at the bend gets hot. Now imagine that paperclip is a world of rock and ice, and the force bending it is the gravity of the largest planet in our solar system. The heat generated isn't just a little warmth, it's a colossal amount of energy, churning away for billions of years, creating a permanent internal furnace. This tidal heating is the engine. It's powerful enough to keep the rocky mantle warm and, crucially, it's more than enough to melt the bottom layers of the thick ice shell above it. This became the only explanation that fit the evidence. The youthful surface, the cracks, the chaos, it all pointed to an ice shell that was separated from the rocky core below, lubricated by a liquid layer. But this was still an indirect explanation. Scientists needed something more direct, a clearer signal that a liquid layer truly existed. And in the late 1990s they found it. The magnetic smoking gun. As NASA's Galileo spacecraft continued its tour, it performed a series of daringly close flybys of Europa. On board was a sensitive magnetometer designed to measure magnetic fields. Jupiter itself has a gargantuan magnetic field. Scientists expected Galileo to simply measure the predictable characteristics of Jupiter's field. But that's not what happened. As Galileo swooped past the moon, its instruments found something unexpected. There was a second magnetic field, a weaker one, embedded within Jupiter's larger field. And this second field was changing, flipping its direction in perfect sync with Jupiter's rotation. This discovery was a quiet turning point. Europa itself was too small and cold to generate its own magnetic field from its core, the way Earth does. The answer came from a fundamental principle of physics known as electromagnetic induction. When you move a conductor, like a coil of copper wire, through a magnetic field, it generates its own magnetic field in response. What Galileo had detected was an induced magnetic field. Jupiter's enormous field was the cause. But for induction to occur, Europa had to have a layer of highly electrically conductive material hidden inside it. A core of molten iron was ruled out. Silicate rock is a poor conductor. But there is one substance that fits perfectly: a liquid ocean of salty water. Imagine you have a metal detector, and you swing it over an empty patch of ground. You hear a steady hum. Now, you swing it over a spot where a large sheet of metal is buried. The detector produces a new signal. Jupiter's magnetic field is the detector. And as it sweeps over Europa, the buried layer of salty water acts like that sheet of metal, creating a new, induced magnetic field. The data was difficult to argue with. The strength and behavior of this field allowed scientists to calculate the properties of the conducting layer. It had to be global, and it had to be relatively close to the surface. The only plausible candidate was a global, liquid, saltwater ocean. More recent data from the Juno mission in 2022 helped refine this picture, suggesting the ice shell averages about 18 miles, 29 kilometers, thick. Beneath it lies an ocean that may be 60 to 150 kilometers deep. Europa, a world smaller than our moon, likely holds more than twice the amount of liquid water as all of Earth's oceans combined. This was the direct evidence. Tidal heating was the theory that explained how an ocean could exist. The induced magnetic field was the observation that proved it did exist. The puzzle pieces had snapped into place. But in solving one mystery, scientists had uncovered a far greater one. An ocean of liquid water, hidden from the sun, on a tiny moon 500 million miles away. The question was no longer if an ocean existed, but what could be living in its dark, cold depths. A recipe for life. With the existence of a global ocean all but confirmed, the conversation was no longer just about geology, it was about biology. Europa went from being a curious icy moon to being the most promising place in the solar system to search for life beyond Earth. For life as we know it to arise, it seems to need three key ingredients: liquid water, essential chemical elements, and a source of energy. As scientists examined Europa more closely, they realized it might have all three. First, the liquid water. This is Europa's headline feature, a vast, stable body of liquid that has likely existed for billions of years. Second, the necessary chemistry. Life needs raw materials: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Europa is a rocky world at its heart, and its vast ocean is believed to be in direct contact with this rocky seafloor. Over billions of years, water would have pulled minerals and chemicals out of the rock, enriching the ocean. Recent observations by the James Webb Space Telescope have even found evidence of ammonia-bearing compounds in some of Europa's geologically young regions. Ammonia is a crucial source of nitrogen, and it also acts as a natural antifreeze, which could help maintain liquid pockets within the ice shell itself. The third ingredient, a source of energy, was for a long time the most challenging part of the puzzle. There is no sunlight in Europa's ocean. Photosynthesis is impossible. But then, in 1977, a discovery on our own planet completely rewrote the rules for life. Deep in the Pacific Ocean, scientists discovered thriving ecosystems clustered around hydrothermal vents on the seafloor, living in total darkness. Instead of using sunlight, the life here used chemical energy, a process called chemosynthesis. This discovery was a revelation. It proved that life did not need sunlight, it just needed a chemical energy source. Suddenly, the dark ocean of Europa didn't look so inhospitable. Given the tidal heat warming Europa's rocky interior, it seemed almost certain that hydrothermal vents must exist on its seafloor. However, recent models from 2026 have added an important layer to this idea. They suggest that Europa's rocky crust today might be too strong to be easily fractured by current tidal forces, meaning its seafloor could be geologically quiet. This doesn't mean vents don't exist, or that they never did. It simply suggests that any active vents today might operate differently from the ones on Earth, perhaps driven by processes that are more steady and long-lived, slowly releasing the chemicals that life could use. So, the recipe appears complete. A vast ocean of liquid water. The essential chemical building blocks supplied by the rocky seafloor and the irradiated surface. And a plausible, sun-independent energy source. This realization is what turned a scientific theory into a global priority. The evidence was too powerful to ignore. It was time to go back. The race back to Europa. The clues gathered by Voyager and Galileo painted a picture of a habitable world, but they were glimpses through a keyhole. To truly understand Europa's potential, we need to go there with instruments designed to answer these questions. And that is exactly what we are doing. First is NASA's flagship mission, the Europa Clipper. Launched in October 2024, this behemoth of a spacecraft is currently on its long, 1.8 billion-mile journey, set to arrive at Jupiter in April 2030. Because the radiation near Europa is so intense, Clipper won't orbit the Moon directly. Instead, it will enter a long, looping orbit around Jupiter and perform nearly 50 high-speed, low-altitude flybys. On each pass, it will dive in, gather a torrent of data, and then swing back out to a safer distance. Its instruments are designed to test the habitable ocean hypothesis. A radar instrument will peer beneath the ice, to finally confirm the ocean's existence and measure the exact thickness of the shell. Spectrometers will create detailed chemical maps of those mysterious reddish stains to finally determine what they are made of. And other instruments will directly sample any dust and gases around Europa. If Europa is venting water plumes into space, as observations have suggested, Clipper could fly right through one, giving us a direct sample of the ocean's chemistry without ever needing to land. But Clipper isn't traveling alone. It will be joined by the European Space Agency's JUICE mission, the Jupiter Icy Moons Explorer. Launched in April 2023, JUICE will arrive at Jupiter in July 2031. While its main goal is to orbit Ganymede, its journey includes two crucial, dedicated flybys of Europa, providing a vital second set of eyes. The 2030s will be the decade of Europa. For the first time, these two missions will work together, transforming Europa from a mysterious, mottled sphere into a world we can begin to know. They aren't designed to find life directly, but they are designed to definitively answer the question of whether Europa is habitable. They will measure the water, analyze the chemistry, and map the energy. They will tell us if all the ingredients are truly there. This entire quiet endeavor, this multi-billion-dollar, multi-decade journey, is all being done to answer one of the oldest questions humanity has asked. Are we alone? The evidence gathered so far suggests that Europa may hold an answer. We began with a mystery, a distant, frozen moon stained with a strange color. We followed the clues, from an impossibly smooth surface to the relentless gravitational dance that heats the moon from within. We uncovered the magnetic ghost of a hidden ocean, vaster than any on Earth. And we found, in the dark abyss of our own planet, a blueprint for how life could thrive in such a sunless world. The journey to this point has been one of humanity's great scientific detective stories. Now, the investigation is entering its final, most exciting phase. As Europa Clipper and JUICE speed toward Jupiter, we are transitioning from looking at the past to building the future. In the early 2030s, the data will begin to arrive. We will no longer have to wonder about the thickness of the ice or the saltiness of the water. We will begin to know. And what if they confirm our greatest hopes? The discovery of life on Europa, even if it's just microscopic, would be one of the most profound moments in human history. It would prove that the spark of life is not a miraculous fluke unique to Earth, but a natural outcome of cosmic chemistry. It would mean that the universe is not a vast, sterile emptiness punctuated by a single, lonely oasis. It would mean that other evolutionary stories are unfolding right here in our own solar system. We stand on the edge of answering a question that has followed us since we first looked up at the stars. The real reason we are returning to Jupiter's moon is not just to study its geology or its chemistry. It's to hold a mirror up to our own quiet origins, and to perhaps, for the first time, find that we are not looking into a void, but at a reflection. The next chapter of this story is not being written in labs on Earth. It is being written across the vastness of space, by robotic emissaries on their way to a small, stained, and impossibly promising world. What it's actually like inside Jupiter's endless storms. From a distance, it is a masterpiece. A world of mesmerizing, endless storms. The soft whites, the deep oranges, and the subtle tan colors all blend together in a planetary dance that has captivated us for centuries. But what if we could look inside? What would we actually find beneath these beautiful, swirling clouds? This isn't a hypothetical trip. This is a voyage guided by real data, by the whispers sent back across millions of miles from robotic explorers like Voyager, Galileo, and most recently, NASA's Juno spacecraft. These missions have given us the physics, the temperatures, the pressures, and the chemical clues needed to piece together what it would be like to journey into the largest planet in our solar system. So let's begin a one-way trip, descending layer by layer through Jupiter's endless storms, from the sunlit, frozen cloud tops to a core so strange it challenges our very definitions of matter. This is the story of what happens when the beauty of the cosmos gives way to the raw power of physics. Imagine beginning a journey, in orbit, looking down at the giant. The Great Red Spot, a storm so vast it remains about as wide as our entire planet, stares back. It's been raging for as long as we've had telescopes powerful enough to see it clearly, observed continuously since the 1800s. Around it, the planet's famous belts and zones, bands of clouds moving in opposite directions, are separated by jet streams moving at over 500 kilometers per hour. From up here, it's all silent majesty. But our mission is to journey into the canvas itself. The descent begins. We can set our starting point at an invisible line called the 1 bar level. It's the altitude where the atmospheric pressure is about the same as the average pressure at sea level on Earth. It's the closest thing Jupiter has to a surface, but it's a surface made of nothing but air. The temperature here is a frigid -108 degrees Celsius. We are above the main cloud decks, in a high-altitude haze. The soft, blended colors seen from orbit are resolving into distinct structures. The quiet view is replaced by an understanding of the immense, chaotic motion that shapes this world. We are now inside the masterpiece, beginning to see the powerful brushstrokes that created it. Our descent continues, plunging past the 1 bar level. We are now officially inside Jupiter's troposphere. The first significant landmark is a layer of clouds unlike anything on Earth. Here we find ourselves enveloped in a thick fog of ammonia ice crystals. This is the highest, coldest cloud deck, responsible for much of the planet's bright, reflective appearance. The temperature hovers around -150 degrees Celsius, cold enough to freeze ammonia into tiny particles that swirl all around. Sunlight, though 25 times weaker than at Earth, still penetrates this high layer, creating a surreal, diffused glow. The majestic bands of color are now vast, continent-sized rivers of weather. We are in one of the zones, the lighter-colored, rising bands of gas. Below, we can see the darker, reddish-brown belts, which are regions of sinking gas. The chemicals responsible for these colors are thought to be complex compounds, dredged up from the planet's warmer interior. From this vantage point, they are colossal weather systems, each wider than our planet, flowing in opposite directions. Even here, the planet is hinting at its complex nature. NASA's Juno mission has revealed strange phenomena, like shallow lightning. Scientists theorize they are caused by a bizarre form of Jovian hail. Storms from deep below are so powerful they can hurl water ice crystals high into the atmosphere. Here, these water ice crystals interact with ammonia vapor, which acts as an antifreeze, creating slushy droplets of ammonia water. These mush balls, as scientists call them, collide and build up an electrical charge, which then discharges as shallow lightning. It's a weather cycle completely alien to our own world. The beauty of the swirling ammonia clouds is a veil, hinting at the incredible forces at work below. As we sink deeper, we leave the ammonia ice clouds behind. The pressure and temperature climb relentlessly, a consequence of descending into Jupiter's gravitational well and approaching its powerful internal heat source. The planet radiates more heat than it receives from the Sun, a remnant of its formation. This internal furnace is the engine that drives its weather. Around a pressure of 5 to 7 bars, we cross a significant threshold. The temperature here reaches 0 degrees Celsius, the melting point of water. We have entered Jupiter's water cloud layer. This is a dense, turbulent region where liquid water droplets form, creating clouds that are the birthplace of Jupiter's most violent storms. It is here that the true scale of Jupiter's weather is unleashed. The rising heat from the planet's interior, combined with condensing water, creates massive updrafts, far more powerful than anything on Earth. This is the engine of Jovian thunderstorms. Data from Juno and Galileo have shown that lightning on Jupiter is common and incredibly powerful. A brilliant flash illuminates the surroundings, a megabolt, hundreds of times more powerful than a typical bolt on Earth. These storms power Jupiter's larger features. Juno's observations have revealed that the Great Red Spot is not just a surface feature. It has roots that penetrate deep into the atmosphere, perhaps as far as 500 kilometers down, far below this water cloud layer. We are in the engine room of the largest storm in the solar system. The environment is a thick soup of hydrogen, helium, and water, with winds that rip through the atmosphere at unimaginable speeds. The last vestiges of sunlight were extinguished long ago. The only light is the brilliant, strobing glare of lightning. As we sink deeper still, something strange begins to happen to the very air around us. Our descent has taken us far beyond the familiar. We are now over 100 kilometers deep. The pressure has surpassed 13 bars, and the temperature is climbing past 100 degrees Celsius. We have entered a region of perpetual darkness where the laws of physics as we experience them begin to change. The atmosphere here is almost entirely hydrogen and helium. On Earth, we can turn a gas into a liquid by cooling it. But on Jupiter, as we descend, both temperature and pressure increase dramatically. We pass what is known as the critical point of hydrogen. Above this point, hydrogen no longer has a distinct gas or liquid phase. It enters a state of matter called a supercritical fluid. It is as dense as a liquid but expands to fill a container like a gas. There is no surface, no boundary. We are no longer falling through air, but sinking through a strange, otherworldly ocean of supercritical hydrogen. The pressure is now mounting at an alarming rate. 20 bars, 50 bars, 100 bars. The temperature climbs to hundreds of degrees Celsius. Outside, there is nothing to see. It is a blackness more profound than any cave, because it is a blackness filled with substance, with immense pressure and searing heat. There are no clouds, no storms, no features of any kind. It is a homogeneous, featureless abyss. We are now thousands of kilometers deep into the planet. The pressure is 1,000 bars, and the temperature is over 1,000 degrees Celsius. And yet, the most incredible transformation is still to come. The hydrogen is on the verge of becoming something even more exotic. The descent continues. We are now thousands of kilometers deep. The pressure has reached an almost incomprehensible 2 million bars. The temperature is a searing 5,000 degrees Celsius, approaching the surface temperature of the Sun. In this unbelievable forge, hydrogen undergoes a profound transformation. Under this colossal pressure, hydrogen atoms are squeezed so violently that their electrons are stripped away, creating a flowing sea of free electrons and protons. In this state, hydrogen stops behaving like a gas and starts behaving like a metal. It becomes an excellent conductor of electricity. We have entered a planet-sized ocean of liquid metallic hydrogen. This is the largest ocean in the solar system, made of the most abundant element in the universe, transformed into a state we can barely replicate on Earth for fractions of a second. The convection currents in this metallic ocean, driven by the planet's internal heat, act like a colossal dynamo. These swirling electrical currents generate the most powerful magnetic field in the solar system, outside of the Sun. And another strange phenomenon occurs here. Helium, which was mixed with the hydrogen above, begins to condense out of the metallic hydrogen like raindrops. This helium rain falls deeper into the planet, a process that helps explain why Jupiter's upper atmosphere is slightly depleted of helium. We are witnessing rain inside a liquid metal ocean, deep within a gas giant. This is the true engine of Jupiter. The heat convecting through this layer is what powers the jet streams and the great red spot thousands of kilometers above. We are inside the furnace that forges the planet's weather. We are now at the threshold of the deepest region of all, Jupiter's enigmatic core. The pressure is climbing towards 45 million bars, and the temperature has soared to over 20,000 degrees Celsius. For decades, scientists had two main theories about what lay at Jupiter's center. One suggested a small, dense core of rock and ice. The other suggested Jupiter might not have a core at all. But when NASA's Juno spacecraft arrived, its gravity measurements told a different, much stranger story. Jupiter's core isn't a small, compact ball. Instead, it seems to be large, fuzzy, and dilute. Instead of a sharp boundary, the heavy elements, the rock and ice, appear to be mixed and spread out, blending gradually into the metallic hydrogen layer above. This dilute core may extend out to nearly half of Jupiter's entire radius, a far larger region than anyone had imagined. This discovery has thrown planetary science into a state of thrilling confusion. One leading hypothesis is that early in its history, Jupiter was struck by another massive object, an impact that would have shattered its original core and scattered its contents. Another idea is that the core has been slowly eroding over billions of years, its material mixing into the metallic hydrogen above. Our journey ends here, not at a solid surface, but in a murky, transitional zone where liquid metal blends with a hot, soupy mix of primordial rock and ice. The very heart of Jupiter is not an object, but a mystery. Our journey has come to an end. From a distance, Jupiter remains a serene work of art. But thanks to the remarkable data from missions like Juno, we now know what lies beneath. We have journeyed through clouds of ammonia ice, witnessed thunderstorms born in water clouds, and passed through a dark abyss of supercritical hydrogen. We plunged into an ocean of liquid metal and glimpsed the central mystery of its fuzzy core, a discovery that is rewriting the textbooks. The story of Jupiter is a story of scale and power. It reminds us that the universe is not obligated to conform to our earthly experiences. It contains worlds where the very definitions of solid, liquid, and gas break down, and where pressures can forge matter into forms we are only just beginning to understand. Studying Jupiter is not just about one planet. It's about understanding the formation of our entire solar system. Its history is deeply intertwined with our own. The discoveries continue, and each new piece of data adds another brushstroke to our understanding of this magnificent and complex world. NASA's Jupiter probe found the unthinkable. In the grand story of our solar system, certain facts felt like stone. They were the foundation upon which we built our understanding. One of these was the nature of Jupiter's heart, a solid core, a dense kernel of rock and ice, the primordial seed from which the king of planets was thought to have grown. It was a foundational piece of our understanding of how giant worlds are born. But a lone explorer from NASA, the Juno probe, hurtling through the most hazardous radiation in our solar system, has sent back a revelation that dismantles that entire picture. What it found is not a solid heart. It is not a neat, tidy sphere. Instead, deep within the crushing depths of our solar system's king, lies a fuzzy, dissolving mystery that seems to defy our best theories. It is a discovery so profound it proves how little we truly know about the giants that dominate our cosmic neighborhood, and it forces us to rewrite the story of our own solar system from its very first chapter. The king of planets, the king of mysteries. To comprehend the meaning of this new discovery, one must first appreciate its subject, Jupiter. It is a world of superlatives, a body so immense it exists on the precipice of becoming a second sun. Its mass is more than double that of all other planets in our solar system combined. 11 Earths could be placed side by side across its equator, and over 1,300 could fit within its volume. Its gravitational influence is a shaping force of the solar system, a quiet guardian that dictates the paths of asteroids and comets, likely shielding the inner worlds, including our own, from countless impacts. From our distant perspective, Jupiter is a masterpiece of celestial motion. A swirling canvas of butterscotch yellows, rusted reds, and creamy whites, painted in belts and zones that circle the planet. These are not static bands of color. They are continent-sized jet streams, moving past each other at hundreds of miles per hour. Dotting this tapestry are colossal storms, some of which could consume our entire planet. The most famous, the Great Red Spot, is a tempest that has been observed for centuries, a storm so persistent it has become an icon of the solar system. For most of human history, Jupiter was just a brilliant point of light wandering through the night sky. It wasn't until Galileo Galilei aimed his simple telescope at it in 1610 that it transformed into a world. He saw not just a disk, but 4 small lights moving in concert around it: the moons Io, Europa, Ganymede, and Callisto. It was a revolutionary observation, the first direct evidence of bodies orbiting something other than the Earth, and it helped dismantle the old geocentric model of the universe. In the centuries that followed, our knowledge grew with our technology. We learned its composition was similar to the Sun's, mostly hydrogen and helium. We saw the violent volcanoes of its moon Io and the intriguing, ice-encased oceans of Europa. Yet for all our observations, Jupiter's true nature remained shrouded beneath its opaque, roiling clouds. We could only see the surface of its weather. What lay beneath, the engine driving its immense power and its unbelievable magnetic field, was a matter of theory, of educated guesses. The deeper we wanted to look, the more Jupiter guarded its secrets. The greatest mystery of all was its heart. The established truth, the solid core model. For nearly 50 years, scientific thought coalesced around a single, compelling narrative for the birth of worlds like Jupiter. It is known as the core accretion model, and it tells a story of cosmic construction that was both logical and well supported by the physics we understood. Imagine the primordial solar system, over 4.5 billion years ago, a vast, spinning disk of gas and dust. In the colder, outer regions of this disk, tiny grains of rock and exotic ices began to adhere to one another. Through countless gentle collisions, they grew from pebbles to boulders, and from boulders to small, primordial planets called planetesimals. The core accretion model proposed that one of these bodies became the seed of Jupiter. As this embryonic world grew, its gravity became increasingly powerful. It began to attract not just other solid objects, but the most abundant material in the disk: hydrogen and helium gas. This process was initially slow. But once the solid core reached a critical mass, somewhere between 10 and 15 times the mass of the Earth, a runaway effect was triggered. Its gravity became so immense that it began to draw in gas from the surrounding nebula at a truly astonishing rate. In a relatively short time, cosmically speaking, it had cloaked its solid heart in a gigantic atmosphere hundreds of thousands of miles deep. This was how the king of planets was believed to have been born. Central to this entire theory was the existence of that initial seed, a small, compact, solid core. It was the necessary first step. This model was elegant, it fit our observations, and it seemed to explain the formation of the other giant planets as well. This wasn't simply a guess. It was based on our knowledge of planetary physics. The immense pressures at Jupiter's center, calculated to be tens of millions of times the atmospheric pressure on Earth, would surely compress any material into a dense, solid state. So, for decades, our picture of Jupiter's interior was clear. A relatively small, solid core of rock and ice, surrounded by a vast ocean of liquid metallic hydrogen, all wrapped in layers of molecular hydrogen and the visible clouds. But science is never truly settled. A clue that the story might be more complex arrived in 1995, when the Galileo spacecraft released a probe into Jupiter's atmosphere. It survived for less than an hour, but it sent back puzzling data. The winds were stronger than expected, and the atmosphere was surprisingly dry. The probe was crushed long before it could approach the deep interior, leaving the ultimate question of the core unanswered. To solve that, a new kind of explorer was needed. The game changer. Enter Juno. To question a consensus that had stood for half a century required an instrument of revolutionary precision. For Jupiter, that instrument was Juno. Launched on August 5, 2011, Juno was a mission conceived for a unique purpose. Its name, from Roman mythology, was fitting. The god Jupiter would veil himself in clouds to hide his affairs, and it was only his wife, the goddess Juno, who could peer through them to see his true nature. This was precisely the spacecraft's objective. The journey itself was an epic of celestial mechanics. After leaving Earth, Juno looped out into the solar system and then swung back past our planet in 2013 for a gravity assist maneuver, using Earth's momentum to slingshot itself toward its target. On July 4, 2016, after a 5-year, 1.7 billion-mile journey, the spacecraft fired its main engine and was captured by Jupiter's immense gravity, entering a long, looping orbit. What makes Juno unique is its orbit. Jupiter is surrounded by the most intense radiation belts in the solar system, lethal to electronics. So, engineers designed a highly elliptical, polar orbit. For most of its 53-day cycle, Juno stays far from the planet. But once per cycle, it performs a high-speed dive, a perijove pass, screaming from pole to pole just a few thousand kilometers above the cloud tops. In a few frantic hours, it gathers a torrent of data and then swings back out into the relative safety of space. Juno's sensitive electronics are protected inside a titanium vault, an armored tank of a spacecraft. And to answer the question of the core, one experiment is paramount: gravity science. Juno does not drill into the planet. Instead, it sees the interior using the language of gravity. As Juno orbits, it sends a continuous radio signal to the deep space network on Earth. The planet's gravity tugs on the spacecraft, causing it to speed up or slow down by minuscule amounts as it passes over regions of slightly different mass. These tiny changes in speed, as small as 0.01 mm per second, cause an almost imperceptible Doppler shift in the frequency of the radio signal. By precisely measuring these shifts from multiple orbits, scientists can build an incredibly detailed map of Jupiter's gravitational field. This map is a blueprint of how mass is arranged inside the planet. A dense, compact core would create a very specific signature. The science team knew exactly what they were looking for. The moment of discovery, the data that broke science. With each perijove pass, each dive through the radiation-laced space above Jupiter's clouds, Juno meticulously collected its data. The radio signals, encoded with the secrets of Jupiter's gravity, traveled 500 million miles to Earth. There, they were sent to science teams at NASA's Jet Propulsion Laboratory and the Southwest Research Institute. The process was painstaking. The signals were faint, and the data had to be cleaned to isolate the infinitesimal Doppler shifts. The expectation was clear. As the gravity map became more refined, a picture should emerge showing the unmistakable signature of a small, dense object at the planet's center. The first few orbits provided incomplete data, but as the mission continued, orbit after orbit, the map grew sharper. And a sense of deep confusion began to spread among the scientists. The signature emerging from the data was not what was expected. The gravitational map simply did not align with the models. No matter the configuration, the team could not reconcile the incoming data with the presence of a small, solid sphere at the center. The mass was simply not concentrated enough. The gravitational pull was more spread out, more diffuse, as if the very heart of the planet was less of a distinct ball and more of a smear. It was a moment of scientific whiplash. The primary goal of the gravity science experiment was to characterize the solid core. Instead, it was revealing that such a core might not exist, at least not in the way anyone had imagined. This wasn't a minor adjustment to the theory. This was a fundamental contradiction. The team checked and rechecked their data. They ran the models again and again. But Juno's instruments were performing flawlessly. The spacecraft was telling them something profound. The data revealed that the heavy elements, the rock and ice that should have been locked in a central ball, were not confined to the center. Instead, they were mixed and distributed outwards, blending into the layers above them over a vast region. The sharp boundary that every model had predicted simply wasn't there. Jupiter did not have a solid heart. It had something far stranger. It had a fuzzy core. The fuzzy core revelation. The term that emerged to describe this structure, the fuzzy core, sounds almost simple, yet it describes a physical reality that is deeply complex and alien. It does not imply that Jupiter lacks a core. Rather, it suggests the core is not a discrete, solid object, but a vast, dilute region, a bizarre, transitional zone where heavy elements are not cleanly separated from the hydrogen and helium above. Consider a cube of sugar dropped into hot tea. At first, it is a solid object. But slowly, it begins to dissolve, its essence blending with the surrounding water, creating a gradient. This is an analogy for what scientists now believe is happening inside Jupiter. The core seems to be partially dissolved into the immense ocean of liquid metallic hydrogen that surrounds it. The scale of this is staggering. Where old models predicted a core perhaps the size of Earth, Juno's data suggests this fuzzy, mixed region is an enormous transitional zone extending over a significant portion of the planet's interior. It is a core without a clear edge. It gradually fades into the next layer up. Within this zone, scientists estimate there are between 10 and a few tens of Earth masses worth of heavy elements. But instead of being packed together, they are diffused, creating a thick, dense soup of rock, ice, and exotic fluids. This revelation forces us to reimagine the entire interior. A journey down would be a descent into unimaginable physics. You begin in the outer atmosphere of ammonia ice clouds. As you descend, pressure and temperature skyrocket. The hydrogen gas is compressed so intensely that it becomes a liquid, forming the largest ocean in the solar system. Deeper still, perhaps halfway to the center, the pressure becomes so extreme that electrons are squeezed from the hydrogen atoms. The liquid hydrogen begins to behave like a metal. This churning ocean of liquid metallic hydrogen acts as a colossal dynamo, generating Jupiter's powerful magnetic field. And then, you reach the core region. This is where the old picture ended with a solid surface. But we now know it is a fuzzy boundary. Here, the metallic hydrogen is enriched with a gradient of heavier elements, a vast, murky zone where rock and ice are suspended and mixed within the exotic fluid. Whether a small, solid kernel exists at the absolute center is still unknown, but it is clear the dominant feature is this enormous, dilute region, a structure no one predicted. The big question: how did this happen? The discovery of a fuzzy core did not merely alter a detail, it challenged the very mechanism of the core accretion model. A spread-out core doesn't have the concentrated gravity to trigger the runaway gas accumulation that was thought to have built the planet. This forced a fundamental question: how did this structure come to be? Two primary narratives emerged from the scientific community. The first was a story of cosmic violence, the giant impact theory. This hypothesis suggested that Jupiter did form with a neat, solid core, but early in its history, a catastrophic collision occurred. Another massive protoplanet, perhaps 10 times the mass of Earth, slammed into the young Jupiter. The energy of this impact would have been unimaginable, shattering Jupiter's primordial core and violently mixing its contents with the overlying metallic hydrogen. We see evidence for giant impacts elsewhere, such as the one that likely formed our Moon. For a time, this was the leading explanation. Recently, however, a team of researchers from Durham University, in collaboration with NASA, used the Dirac-Cosmos supercomputer to model these titanic collisions in unprecedented detail. The results, published around August of 2025, were a major turning point. The simulations showed that even a colossal, head-on impact could not create a permanently fuzzy core. While the impact would shake the planet, the heavy materials from the shattered core would resettle toward the center due to gravity, reforming a distinct core in a surprisingly short time. A stable, long-lasting dilute core was not a possible outcome. This cast serious doubt on the giant impact theory and elevated a second, more radical idea. Perhaps the core was never solid to begin with. This gradual growth model suggests the process of Jupiter's formation was messier than the clean, two-stage core accretion model allowed. Instead of a solid core forming first and then grabbing gas, Jupiter may have grown by accreting gas and solid planetesimals simultaneously. As these rocky, icy bodies plunged into the growing planet, the immense pressures and temperatures would have vaporized them, allowing their material to mix directly into the gaseous envelope. In this scenario, a fuzzy core is not the result of a later catastrophe. It is the planet's natural, primordial state. A solar system-wide revelation. The implications of Jupiter's fuzzy core would be profound on their own. Yet what makes this discovery truly revolutionary is the growing evidence that Jupiter is not an anomaly. It may, in fact, be the standard. Evidence now suggests that Saturn, our solar system's other gas giant, also possesses a fuzzy core. This discovery came from an incredibly clever analysis of its most famous feature, its rings. Data from the Cassini mission revealed subtle ripples in the planet's inner rings. Scientists eventually concluded these were caused by oscillations inside Saturn itself. The planet is constantly, subtly, quaking, and its sloshing interior creates tiny fluctuations in its gravitational field. These pulses ripple outwards, disturbing the ring particles and turning the entire ring system into a giant seismograph that lets us probe the planet's deep interior. The models that best explain these ring ripples all point to the same conclusion. Saturn, like Jupiter, has a large, dilute, sludge-like core. The fact that both of our solar system's gas giants appear to have this strange structure makes a random, catastrophic impact a less likely explanation for both. The coincidence would be too great. Instead, this parallel discovery strongly supports the idea that forming with a fuzzy, diluted core might be the standard way that gas giants are built, not just here, but across the galaxy. Every one of the thousands of giant exoplanets we have found may have a similar internal structure. The unfolding mystery. The story of Jupiter's core is a quiet testament to the scientific process itself. We began with a logical and elegant theory that stood for decades. We built a machine, the Juno probe, to go and confirm it. But instead of simple confirmation, the universe sent back a riddle. It gave us data that shattered our old certainties and replaced them with a far stranger, more complex, and more fascinating reality. Jupiter, the familiar striped giant, has shown us that it is more alien than we had imagined. The journey is far from over. Juno's mission has continued to yield data well past its original timeline, with findings as recent as early 2026 further refining our models of this bizarre interior. And it will not be the last visitor. The European Space Agency's JUICE mission is on its long journey, set to arrive in 2031 to study Jupiter's icy moons. China's Tianwen-4 mission, planned for launch around 2029, also has Jupiter in its sights for a 2035 arrival. Each will build on Juno's legacy, adding new pieces to this puzzle. What Juno has taught us is that the universe is under no obligation to conform to our expectations. Its greatest secrets are often hidden, waiting for the right tool and the right moment to reveal themselves and remind us that the age of exploration is far from over. The truth is out there, written in the language of gravity and light, and our quest to understand it is just beginning. If you believe that science and exploration are essential to understanding our place in the cosmos, be sure to subscribe and join us on this journey. New discoveries are being made every day, and we will be here to explore what they mean. Let us know in the comments what you think about Jupiter's fuzzy core, and what mysteries you feel we should explore next. Thank you for watching.